cut off of my.
Yeah, so there'll be a chair. Actually, there'll be a chair, the session chair who'll look after that. So yeah, and I think probably what is being done is, at least that's what was done yesterday, that you probably get a tinkle maybe 20 minutes into your talk or something like that. That so that you know, like you have 5 minutes more to go, something like that. So you'll have a reminder.
Yeah, that's fine.
Ramadevi is the chair, so she'll. I don't know if she's no, she has to join. So. Hi, Chandrasekhar जी, कैसे हैं आप?
All well. Nice to see you.
Yeah, well, nice to hear you. Is all I can say. I don't see you.
So Sergei, I see two big rooms. Where are they? Just out of curiosity.
Yeah, sure. One is in the International Center for Theoretical Sciences, Bengaluru. And the other is this Institute of Science, Education, Research, Bhopal. So one down south, one in the central part of India.
I see. Yeah, I visited one of them, I believe. Yes.
I think must be Bengaluru, probably.
Yes.
One down south. Yeah. So it must be cold in Pasadena now.
Oh yes, it's especially by California standards.
You don't get snow, right? I mean, you guys don't get snow.
Well, there is snow in the mountains. We're a few kilometers away from the mountains, and like 10 kilometers, and up and there is snow. Yeah.
You got this black-colored mountain somewhere near the campus, right? I mean, what is that? I mean, I've been there just once, so I remember this. So what is that?
Well, there is Mount Wilson right next to the campus, where
it must be that.
Yeah,
pretty dark in color.
Well, now it has white caps, so it does have snow.
Okay.
Yeah.
Okay.
So, because it's been raining here last week and snowing in the mountains.
Oh, okay.
Yeah, so you should visit again and see it in different color.
Yeah. Okay, so do we see? Hi, Sunil. How are you doing?
Hi, Sunil. Yeah, it's been a long time since I saw Sunil.
Does California have any?
Hi, sorry.
Yeah.
Oh, nice to see you.
Yeah, hi, Sergei. How are you?
Good. How are you?
Nice to see you? Yeah, good. Thanks.
I was saying that it's been a while since I saw you in person.
You're right. I mean, I haven't been to California in maybe 20 years, I think.
But even at conferences, I guess we maybe saw each other 5 years ago. So
yeah, I was at Okinawa. Were you there?
I don't remember, but yeah, that's roughly around the time of 5 or so years.
Yeah, it's really unfortunate we missed all the good places for. I mean, Okinawa was great, but many good places for strings meetings became virtual, and then it was no fun. I was dying to go to Brazil or to also to Cape Town.
Yeah, me too. We can try to repeat. So hopefully this locations will agree to give it a second chance.
Yeah, especially since they didn't have to organize the physical meeting the first time. So yeah, they will, I think.
Yeah.
Some of us are saying that they haven't received the Zoom link. I mean, I'm not sure what is meant by receiving because it's all there on the website. What are you saying?
I'll just come back. Shouldn't we be starting, Alok?
Yeah, that's a funny thing. I'm getting emails that people do not know what the link is, but I thought it was made amply clear that you have to refer to the website. It's all given.
Yeah, but I think the website does have a slight problem because it took me a while to access that Zoom and YouTube links.
Oh, okay. So I have sent that information on the Google group, and now I'm going to copy that information.
Yeah, I've got that. So
I'm going to copy that information to all the 369 registered attendees, participants.
I think the website got a little stressed out probably with everyone accessing it.
I see. Okay, so I did not know that. Okay, so.
But the number has grown rapidly in the last few minutes.
I see. So,
but where's the chair?
I had trouble logging in. Yeah.
Rama is probably the same issue.
Hi, Abhijit. Good morning.
Hi, Sergei.
Hello.
Oh, sorry, I was on mute. I said hi.
Well, hi to everybody. But
Rama is not here. Oh boy. See, what do we do about that? I hope she would have gotten the email.
Alok, maybe if Abhijit agrees, he could swap with Rama as chair.
Yeah. I mean, I have no issues. Absolutely. ऐसा करना सही रहेगा?
Okay, so I need. Yeah. Okay. Let's see.
उत्तर मिल गया.
Yeah, we could do that. I just have to recover this sheet that we had sent.
Yeah, or I mean, you just access the website. Everything is given there.
Okay.
Yeah. Important that we should start right away, I think.
Okay. All right. So.
Yes. Sergei, do you want to share your screen? Let me turn the screen on. Sorry, no, I'm not the host here. It must be on. Yeah.
Team, can we have Professor Abhijit also as a co-host?
Yes, sir.
All right, Abhijit. I don't see Abhijit as co-host. Can you do that quickly, please? Yes, good to go. All right, so maybe Abhijit, just a little. So we have a slight modification in the session chair. So we've got Abhijit. Rama is maybe decided to join or something. So obviously, welcome to day 2. I forgot to say that. And I'm given to understand that apparently has some issues with the website in terms of accessibility. Maybe it got overloaded in terms of accessing. So, but I don't know. I mean, all links, everything are given there. But now, as I was pointed out by Suresh, I think I should send across explicitly the Zoom links, at least on the ISM Google group, and also this group email ID of ISM21 registrants. So I think that should probably cover it. I did not anticipate this. I wasn't even aware that this is going to be an issue. So I'm going to take care of that. But anyways, I think we all have the info now. So I think that we already 5 minutes past. So I think let's start. Abhijit, please.
Hello, everyone. Hi, Sergei. So today's your talk is going to be for about half an hour. Well, for half an hour. So usually we split it as 25 minutes plus 5 minutes questions. But of course, if we have questions during the talk, then we could shuffle the time around. Okay, so let me welcome everyone, and let me say that today we are very happy to have Professor Sergei Gukov from Caltech, and he's going to tell us about higher form symmetries in TQFTs and Coulomb branches. Over to you, Sergei.
yes, thank you so much to everyone, to the organizers, for putting this meeting together and their hard work despite all the difficulties and challenges that we're facing, including the technical ones. I also want to thank Abhijit for stepping in and hosting me. This is actually my second time visiting India in the last couple of months, and Abhijit is being the host, both of them, so it's a pleasure, and I hope to come back, hopefully in the near future. So what I'll tell you about in this half an hour or so is snippets of work that we've been doing with various collaborators, and it's mostly based on these two recent papers, which share mathematical content. It's roughly half of the work, and today I'll focus on the other half, which is for today will be exclusively physics component, and some of the collaborators here are split among physicists and mathematicians also fairly evenly. So for instance, in our physics community, you probably know many faces, even mathematicians such as Hirako Nakajima. Probably less known to you is Francois Costantino, who is an expert on fairly exotic so-called non-semi-simple TQFTs, which until recently had not really appeared in string theory or quantum field theory community. And these two papers are basically devoted to bringing this kind of TQFTs in light. And I'll try to explain why they're interesting or delicate, even from the TQFT point of view. So the main theme of the talk will be symmetries, and symmetries will play a sort of double role in this talk. So they'll be very important for solving certain problem or helping us with a certain issue. That's one aspect. But in the same time, symmetries will make certain things delicate and more interesting. So on the one hand, they'll come and solve for a certain problem, but on the other hand, they'll introduce additional layer of complexity, which in my opinion is not really complexity, but makes story richer, more interesting. And keep in mind this two roles that symmetry will play in this talk. And the other, or physics goal of the talk in some sense, is to understand super conformal field theories. In my case, it will be three-dimensional and equals four theories, but could be something more general, for example, 4D super conformal field theories or 2D super conformal field theories via the moduli spaces. The most popular types of moduli spaces or vacua involve Higgs branches and Coulomb branches, parameterized respectively by either vevs of matter fields or fields in super multiplets for her gauge field SIDS. And these are Higgs branches and Coulomb branches, which in 3 dimensions also split their role in a way that Higgs branch is typically simpler, especially with this amount of supersymmetry, whereas Coulomb branch still remains delicate and interesting. For instance, chiral ring of operators on the Coulomb branch and such theories involve monopole operators, which is one of the most interesting aspects in this kind of theories. And the goal is to understand, first of all, Coulomb branch, and then use information about these branches to sort of bootstrap or say something about strongly interacting conformal field theories. That's the motivation. But even Coulomb branch itself often turns out to be quite interesting and delicate, and there are several ways to deal with this issue. One is to seek various dualities which map Coulomb branches into Higgs branches of different theories. This is known as three-dimensional mirror symmetry. Or try to tackle strong coupling effects which are protected by supersymmetry. For example, one can try to explore these monopole operators, study the chiral ring in general, and this gives information about this moduli space, the Coulomb branch M, via basically accessing its coordinate ring of holomorphic functions, or if we prefer to work with some function or number rather than space, you can ask about the Hilbert series. So that's a simple kind of function that encodes information about the chiral ring. and it was actively studied in many recent years. For example, by Ami Hanani and collaborators and by various other groups. So developing various techniques how to compute, for instance, either coordinate ring or the Hilbert series. So this is the basic information about the Coulomb branch, and this is going to be the star of the show in the rest of the talk. One aspect which from physics point of view is completely obvious and does not deserve much time or attention is the fact that Coulomb branch is always non-compact. So this doesn't present any question from physics point of view, but in a moment it will present, it will be important. It will present a certain technical difficulty. So the point is that to every Coulomb branch, or more generally moduli space with the same properties as such Coulomb branches of 3D n equals 4 theories, you can associate a three-dimensional TQFT. So that in that same 3 dimensions where we discuss our 3D n equals 4 superconformal theory. And in that TQFT, these two ingredients, namely the ring of functions on a Coulomb branch as well as Hilbert series, appear as basic building blocks. Namely, the Hilbert space on a sphere is exactly this ring of holomorphic functions, and invariant associated to S1 cross S2, roughly the trace over this Hilbert space, is precisely the Hilbert series of the Coulomb branch. So the fact that in this three-dimensional TQFT, Hilbert space on a two-sphere is a commutative ring is fairly easy to see by visualizing the following. So you think about two-sphere to which this Hilbert space is associated, and construct a big three-dimensional ball from which you excavate two smaller three-dimensional balls. Then what it does, it provides a map from two copies of the Hilbert space of a two-sphere, because there are two boundaries inside, to another one, and that's exactly the product in this commutative ring. And it's also commutative because you can interchange these two smaller spheres, and their order does not really matter. So that's how you see the commutative ring structure. Now, we mentioned a moment ago that Coulomb branches are always non-compact, and this will lead to interesting feature of these three-dimensional TQFTs to be, on the one hand, not quite TQFTs in a standard sense. They'll be funny, or more technical name is logarithmic, that already showed up on the first slide. And in the same time, symmetries will play an important role. So they'll be decorated or enriched in the terms of condensed matter physics by additional symmetries. So any questions so far? Okay, if not, I'll proceed. So the three-dimensional TQFT that I have in mind in the previous slide is a theory introduced by Rosansky and Witten. So they proposed how to make a three-dimensional twist of such 3D n equals 4 theories. And the twist leads to precisely the properties I mentioned on the previous slide. In fact, the moduli space did not have to be a Coulomb branch. It could be a general hyperkähler manifold, or even more generally, some holomorphic symplectic manifold. But for today, think of it as a three-dimensional Coulomb branch, which is going to be useful for many things I'll try to say later. This topological quantum field theory is mathematically well defined. So shortly after the work of Rosansky and Witten, it was formalized by Kontsevich, and also independently by Misha Kapranov, who used IT classes. So now this three-dimensional TQFT also exists in a strict mathematical sense. However, it exists for compact target spaces or compact manifolds. So here, Rosansky and Witten call moduli space by capital X. So I'm going to adopt their notations. And when X is compact, such as K3, for example, everything is fine. And that's indeed where we have this mathematically rigorous definition. But throughout the paper, Rosansky and Witten point out a number of times that when X is non-compact, we have to be extremely cautious. And in particular, if we try to study this Hilbert space that I mentioned before, associated to various surfaces of various genus in this TQFT, then analysis could be hazardous at best if X is non-compact. And that's exactly the issue that we're going to deal with in this talk. So that's the catch. So on the one hand, Coulomb branches of such theories are always non-compact, and therefore it seems like an important challenge to tackle. So here is an explicit form of the Hilbert space, also taken from their paper. Here you can see very explicitly that indeed, for example, for two-sphere, when we ask for Hilbert space of this TQFT on a two-sphere, it's simply a space of holomorphic functions on the Coulomb branch, and more generally space of holomorphic forms. But again, if Coulomb branch is non-compact, that's going to be infinite dimensional space. So that's the problem. That's the challenge.
Sorry, Sergei, what is V in this slide?
V here is, I believe that, yeah, so here is a holomorphic tangent bundle of X. Yeah.
Thanks.
Yeah, sorry. Yeah. I just literally copied the formulae from their paper. Thank you. So another player that will somehow show up later in the talk is modular structure. It's not going to be as important as symmetries or other ingredients I mentioned, but this is something that's good to keep in mind, especially in connection to two-dimensional conformal field theory. So the reason is that in the case of theory like Chern-Simons theory, for example, the dimension of the Hilbert space on a genus G surface is closely related, and in fact can be expressed in terms of modular data, so-called S metrics of the corresponding two-dimensional CFT. So that's a famous Verlinde formula. And the same procedure works for many three-dimensional TQFTs whose Hilbert space on genus G surface is finite dimensional. This is a fairly general phenomenon. You can associate modular data to three-dimensional TQFT, and therefore S metrics will show up and encode dimension of the Hilbert space. But the situation that we're dealing with involves infinite dimensional Hilbert space, as we just saw a moment ago in our three-dimensional TQFT. So a natural question will be, what's the analog of this Verlinde formula? We can't literally just take the dimension of it because we'll get infinity. So we'll have to regularize it in some form. And I don't know how to answer this challenge posed by non-compactness of the Coulomb branch in general, but what I'm going to propose in this talk, based on this work with Nakajima and others, is to use symmetries to consider equivariant version of this regularized sum. So this will provide regularization, and it's true that Hilbert space will be infinite dimensional, but as long as there is a symmetry that allows to split it in finite dimensional graded pieces, then we can form this series introducing corresponding equivariant parameters. I'll call them T, X, and so on in the rest of this talk. So they will provide additional grading and will allow us to write infinity in a nice way as a power series in terms of this equivariant parameter T. So this trick goes back at least to work of Moore, Nekrasov, and Chatashvili, where they used equivariant integration over Higgs branches. So what we'll be doing is a basically Coulomb branch version of that. And many other works before we implemented it with DU in exactly this sort of context that will be relevant to us. These days, similar equivariant regularization is also used in many other TQFTs in other dimensions whenever the Hilbert space turns out to be non-compact. For instance, in the work of Tanaka and Thomas, it's used to regularize 𝗰𝗶𝗶𝗏 partition functions. It can be used to regularize multi-monopole Seiberg-Witten systems in four-dimensional TQFT based on this multi-monopole equations and so on. So symmetry will be of our help here. And the formula that we propose for analog of the modular data, where the sum over this labels lambda is still going to be a finite sum is such that given a Coulomb branch, which again, following Rosansky and Witten, I'll call X, the claim is that the sum can be still expressed in terms of finite dimensional data of fixed points. So I'm going to denote fixed points of symmetry. Let's say there is a U1 symmetry, it could be larger in general, acting on the Coulomb branch. So lambda will be labeling the fixed points, and then geometric data at a fixed point will determine the matrix elements of T matrix and S matrix, very much like in the usual modular tensor category or modular data of conformal field theory, so that you can use this data now to produce this equivariant version of Verlinde formula or invariance of 3 manifolds. And once you have a symmetry, let's say U1 symmetry with the equivariant parameter T, a general holomorphic symmetry acting on such Coulomb branch will have, first of all, moment map, because it's Hamiltonian, so a moment map I'll denote by mu, and it also acts with various weights and normal bundle directions. So assuming that fixed point is isolated, for example, you'll have lots of the whole vector of weights, W, and this information of W and mu determines essentially this enters this matrix element. So the W's enter denominator of this formula, mu, for example, enters the matrix element of the T matrix, and so on and so forth. You can find further details on how to associate additional data in those papers I mentioned. But I want to focus rather on examples, especially since time is short. So,
Sergei, I apologize. Can I just ask this? What you have is square root kx. It's like is a square root of a canonical bundle? I mean, do you have some kind of a spinner in the story?
Well, yes, it's a square root of canonical bundle of this non-compact target space or Coulomb branch X. Yeah, yeah.
So I mean, right. Section. So that would be some spinorial degrees of freedom in your story.
That's correct. In fact, in general, this formula that I'm presenting here, obtained by summing over lambda of this expression, is nothing but counting index of the spin C Dirac operator on target space on this Coulomb branch X. That's correct.
Oh, okay. Thank you so much. Thanks.
Yeah. That's maybe another way to think about it. So instead of, again, outlining the general story and give you further details, let me give you a couple of examples. So hoping that will shed light. So in this first example is where X has hyperkähler dimension 1. So it's a fairly small dimensional manifold with U1 symmetry. With respect to the symmetry, it has 2 fixed points. So there will be the size of this S and T matrices will be 2 by 2. Here is the values of the moment map and the weights for these 2 fixed points, and all these fractions of 1/5 or 6/5 and so on translate into specific elements of S and T using the rules on the previous slide. And what you get is S and T matrices of Fibonacci anyons. So that's one simple example that comes from 3-dimensional reduction of a 4-dimensional Argyris-Douglas theory. Well, if you think about hyperkähler manifolds, this choice of X is not the simplest one. In fact, the simplest one probably that would come to your mind of this smallest dimension would be cotangent bundle to CP1. But this one is actually more interesting and more complicated because the example that leads to this Fibonacci anyons is more generic in a sense. In particular, the weights are fractional. It has only 1 symmetry, whereas T star of CP1 has actually 2 symmetries. And that's going to be important in the rest. One is holomorphic. That's what I just used. That's kind of generic. But the other is a little bit more special. It's holomorphic with respect to all 3 complex structures or symplectic structures. And again, there are 2 fixed points, north and south pole of CP1. So in that sense, it's similar to the previous example. If you work out the normal bundle weights and all the moment maps and everything, you get these values, for example, for the S matrix and similar for the T matrix. So you put it together and you can compute this regularized TQFT, Rosansky-Witten TQFT invariant associated with non-compact space T star CP1 on any genus G surface, in particular on S1 cross S2, which is indeed supposed to be the Hilbert series of T star CP1. So T star CP1 can be presented in many different ways, for example, as a quadric and so on. And you can easily compute its Hilbert series, so indeed it will match this expression. But important difference between this two symmetries, one of which is just holomorphic and the other is actually triholomorphic, is that the holomorphic one cannot be consistent with topological twist on a general three manifold, whereas triholomorphic can. So when you go to more general three manifolds and use these ingredients, for example, of modular data, S and T matrices, you can compute using this S and T matrices invariance of more general three manifolds, but you're obligated to remove variable T, set it to 1. But you can actually still keep variable X on a general three manifold, and then question becomes, what is X? So it turns out that it's playing a very important role. So it's additional decoration of the TQFT. So it's additional structure associated with the symmetry. And if you go through all the details of this twist, you see that it's actually background for higher form symmetry, namely one form symmetry, or even more precisely for so-called spin C structure on the three manifold. So it's labeled by elements of H_2 of the three manifold. So that's the crucial difference between the two symmetries that you could use. And from regularization point of view, both of them would be helpful, but one can survive on a general three manifold, but the other cannot. So this, you can continue playing with many other examples. Of course, I showed you the simplest ones like T star CP1. Of course, you can consider cotangent bundles to Grassmannians, Hilbert schemes of points, and various other interesting metrics, hyperkähler metrics on non-compact manifolds. So all of them correspond to interesting TQFTs, but all of them are non-compact and will require some kind of regularization, which will force us to think about TQFTs, which are not quite usual TQFTs. In fact, they're logarithmic, but they're also equipped with a more general symmetries and structures, very much like this variable X, which showed up a moment ago. And what we're seeing here is in this talk a kind of dictionary or relation between geometry of Coulomb branches and algebraic structures that appear in a TQFT. So I already mentioned modular tensor category. That's something that you can associate to every TQFT, and it's describing braiding and modular data of anyons. And this tensor category also can be realized as a representation category of some vertex algebra or conformal field theories. And what's interesting in examples that arise from such Coulomb branches is that corresponding MTCs are non-semi-simple, and the vertex algebras or CFTs are logarithmic. So that's rather interesting exotic feature of this correspondence. So in the remaining 3 minutes, I hope Chair allows me 3 minutes. I want to go through and I say a few words about the role of this decoration, this additional data that arose from a symmetry that we used in order to regularize partition functions. So this background data or structure associated with the symmetry goes by many different names in the literature. And it's interesting that these names or structures are not really aligned, and people from different walks of life didn't compare, at least until so far, some of these backgrounds or terms that appear in the literature. And from the CFT point of view, we're simply talking about twisted sectors, where we consider vertex operators labeled not only by position on a plane and choice of operator, but also by an element of the group, such as G1, G2, and so on. And from the three-dimensional TQFT, this corresponds to labeling line operators in addition to usual labels by choice of symmetry. So to illustrate what this means, in this recent paper with Francois and Pavel, we discussed a very simple example as a warm-up. So just usual familiar U1 level K Chern-Simons theory. So this theory has usual zero form symmetry, nothing fancy yet, it's just zero form symmetry U1 or C star if you prefer to work with holomorphic in a holomorphic setting. And the symmetry is simply described by connection, background connection, which couples to the first Chern class of the U1 gauge bundle. So C1 is the first Chern class of gauge bundle, omega is a choice of H1 on a 3 manifold, and here it's valued in G because that's our symmetry. Important point from TQFT point of view is that Hilbert space in such setting is first of all decorated by this symmetry. So for instance, if your surface is sigma, then you have to choose elements of H1 of sigma with values in this symmetry group G. But in order to ensure cutting and gluing properly, you also have to consider additional structure from H2 of sigma. And that's additional grading, which involves Pontryagin dual G hat of the symmetry group, in our case U1. So this example is extremely simple, and of course it's a free theory, but it's very illustrative for generalizations. So here in this three-dimensional TQFT, the category of line operators for any choice of group element G has K objects. So there are K lines in U1 level K Chern-Simons. But when things are twisted by this G, these charges of line operators are shifted, and line operators themselves, even though they define in the usual way, they're always attached to the boundary of a surface operator, which becomes, if you try to run this line operator into the boundary, the usual twist operator in the from the twisted sector, in this case, G twisted sector of the corresponding boundary condition. So this is going to be the last slide. So just to summarize, I explain a little bit how this G symmetry shows up in TQFT. It provides very delicate and important information of decoration and grading for Hilbert spaces and plays an important role of cutting and gluing, which I didn't have time to discuss. But what we saw earlier is actually analog of this for one form symmetry, which is closest to this spin C structure that emerged from using triholomorphic symmetries in Coulomb branches. And this likewise gives rise to additional data of decorations and gradings where degrees are shifted the way you'd probably expect it to be. But again, Pontryagin dual shows up and plays a role. And the reason we needed this analysis and go down the rabbit hole of analyzing the symmetries is because we encountered a relation between TQFTs, which on the one hand are decorated by H1 elements and correspond to the usual zero form symmetry, just like in U1 level K Chern-Simons that I showed. But on the other hand, they're related to this spin C decorated TQFTs, and relation between them involves a version of Fourier transform, which changes degrees of these forms on the slide, but also involves spin structure on one hand, but not on the other. So this is basically a version of Bosonization in the world of TQFTs. So that's the real application why we needed this. And I want to thank you for your attention. And yeah, thank you.
Thank you very much, Sergei, for a wonderful talk. So let me ask if we do have a couple more minutes. So let me see if people have any questions. Yeah, Alok, go ahead, please.
Yeah, hi, Sergei. I just have a very general question. So if you look at modular space of flat bundles with non-compact gauge group, I mean, can some of the ideas you described be used to quantize it in the in your initial part of the talk?
Yes, that's. Yeah, so yeah, hello. So that and thanks for this question. The short answer is yes. In fact, the idea here in this equivariant regularization of Hilbert spaces that led later to equivalent Verlinde formula and many parallel developments is precisely indeed aimed to develop the rules of cutting and gluing in TQFTs, where, for instance, the Hilbert space comes from quantizing non-compact phase space or moduli space of some connections or structures which is intrinsically non-compact. So the idea in such approach or such setting is typically to understand very well how things behave on S1 cross-Riemann surface.
Yes.
And once this is done, so once you have this sort of equivalent Verlinde formula under control, you can actually proceed to talk about S and T elements. And this already is the door to most general modular tensor category, which relies on this modular data. Yeah.
Thank you. Abhijit, can I just ask a small follow-up?
Sure, please.
So in the case of the modular space for the compact gauge group, we have this idea that index of the Dirac operator is the quantization, right? So is there a similar interpretation if I did, if I quantize modular space of flat bundles on a Riemann surface with boundaries, but with non-compact gauge group? The fact that quantization is the index of the spin C Dirac operator.
Yeah, I think it's good, at least to first approximation, you can think that it's very similar. The only question is that now formally this index will be infinite dimensional. For example, if you think mathematically about the index as virtual space, vector space, or complex, this complex is going to be infinite dimensional. So that's why the symmetry is important. It's providing additional grading to this infinite.
I see. It just splits the sum into the infinite sum into the sector.
Yeah, exactly. It splits into finite dimensional pieces. Of course, there are infinitely many of them, but as long as each piece is finite dimensional, we're in a good shape. So that's the idea. Yeah.
Okay, thank you.
Okay, so before we move on to the next speaker, let me ask a small question. So, Sergei, people sometimes couple non-dynamical sectors to non-topological sectors to topological theories, such as in talking about Chern-Simons matter theories. So, can such a thing be done in this context?
That's a very good question. So usually, right. So they probably do it most of the time in the case where ambient background is flat, so we consider something basically as a flat space, because, as you say, the other sector is non-topological, so it's probably better to consider it just in flat space. Or
the sphere also, for example, people consider.
Yeah, on special, rather simple free manifold. Yeah, so that's a very good question. I don't know if coupling to such, so that's true. Examples like I've seen, for example, in the case of duality appetizer and simple theories like that, one usually finds a coupling to rather simple TQFT, which is quote unquote small. So it's a very light, simple thing. So these TQFTs I described here today are very heavy in the sense that they have infinite dimensional Hilbert spaces. So I haven't seen such an example, and it's an interesting question. It would be good to either find it or maybe even construct and see what happens, because I don't think we have experience of coupling this sort of TQFTs to usual QFTs.
Right.
Yeah, very, very good question. I have no good answer, but worth exploring.
Thank you. Okay, so at this juncture, let me request the original scheduled chair of the session to take over. Please, Professor Ramadevi, over to you. And I will also, sorry, go ahead. You are on mute, Rama.
Yeah, I don't know. The Zoom didn't connect at 9:25, and now I rebooted my machine. It's connecting me to a different background. I don't know in which country I am and which city I am. Are you all able to see me in a different background? I really don't.
It's a lovely background. Given the winter here, it's very refreshing to see that.
I'm sorry. I don't know. The network really bothered me. Anyway, now I'm fine. Yeah, thanks, Sergey. I missed the initial parts of your talk. Probably I saw the last 20-25 minutes. I had a small question. The sigma G cross S1 partition function, has anybody done the large N expansion and written like the 2ft expansion? Anyone has done this?
Yes, I think questions like this come up in the study of ADS4 black holes.
Like about 20 years ago, I struggled a lot, but I didn't fix it. So
Yeah,
I wanted to...
right now I think it's yes, it's being explored, at least in some cases. Typically with simpler versions of these TQFTs, and again, they don't really require very general 3 manifolds as backgrounds, but 3 manifolds that are natural in the context of ADS4 black holes. So in that case, one can indeed consider such partition functions and study large N expansion. Yeah.
So those days, the Vipul Periwal had a neat expansion for sigma 1 cross S1. But yeah, so for a sigma G cross S1, I struggled a bit, but I have not still succeeded. Maybe I'll take a look at these references. Which are
Yeah, I think in general, in this context, there is a lot to be done, even with large N expansion and exploring some of these more exotic theories with logarithmic MTCs or symmetries. So such exotic TQFTs, for example, they didn't propagate into our QFT world until recently. So I think there is more to be done. But I also don't want to delay the session further. So maybe
yeah, we can.
I'll be glad to answer questions over email as well.
Yeah, sure. Anybody else has any questions? Otherwise, we can thank Sergey again for this nice talk. And we can. Anyone else? I'm missing anybody? Okay, so let's thank Sergey again. And the next speaker for this is Sujay Ashok. Are you able to share the screen now, Sujay? Can you try to share your screen?
Try now.
Yeah.
Can you see?
Yeah. Sujay is from Institute of Mathematical Science, and he will tell us about ADS3 cross S1 chiral ring. Yeah.
Thank you. Right. So thank you to Alok and the team at IIT Roorkee for all their hard work. Right, so I'll report on work done with Songyuan Lee and Jan Trost. Jan is my permanent collaborator for the last many years, and Songyuan is his former student who is now a postdoc in Greece, I think. Right, so let me begin with some context for this work. So the context is ADS3 CFT2 for backgrounds that have NS flux. So this is a very well-studied background, especially in the last few years. And a nice review talk by Rajesh about this yesterday. So the approach is sort of powerful because the worldsheet CFT that describes this background with NS flux is exactly solvable in alpha prime. The ADS3 part of the background is described by a Witten model with gauge group SL2R at some level K. And this K sets the scale of the ADS of the curvature in ADS space. So large K essentially amounts to semi-classical gravity. So because we have this powerful worldsheet framework, the idea is to use worldsheet methods to obtain whatever information one can about the bulk ADS3, about strings in ADS3, as well as therefore the dual boundary theory. Okay. So the theories that are best studied have n equals 4,4 supersymmetry, either large or small. And in the last few years has seen an amazing amount of progress, especially due to work by these authors, Bahat, Gabadiel, 𝗬𝗫𝗀𝗀𝗀, Knighton, and so on. But in this talk, the goal would be to focus on ADS backgrounds with lower supersymmetry, especially 2,2 supersymmetry. So we'll focus on backgrounds that we like to call ADS3, S1, and Y. So I mean, we call it ADS3, S1, and Y, but there are some 4 fermions that make sure that you have n equals 2,2 supersymmetry in space-time. And the S1, it just takes care of the fact that the 2,2 theory on the boundary has the U1R symmetry in the global algebra. And one can check that this model is a critical string background when the central charge of this compact Y theory takes the form 9 minus 6 pi k. So this k is again the level of the SL2R. So there are various examples one can do. I mean, for instance, if you take Y to be a minimal model, a supersymmetric minimal model, and T4, you get back the n equals 4,4 supersymmetric theories. So we will often check our results by putting this particular Y to make sure that we recover all the known results. But you could just take something like Y to be a sum of 3 minimal models at some levels ki, such that their inverses add up to 1 by k. So these are all simple examples. But in general, the goal is to see what one can say about such n equals 2 models and how, especially why, how what we compute depends on Y in one particular manner. Now, the worldsheet theory on Y has to be, so this is the worldsheet theory. So the worldsheet CFT has to be 2,2 subconformal in order for the space-time theory to have 2,2 supersymmetry. I hope this point is clear. So I'm hoping to describe these space-time or boundary theories with 2,2 supersymmetry. And as a requirement, we need to construct the global superconformal algebra in space-time. And for that, Givion and Pacman back in 2003 showed that this Y model, this worldsheet theory on Y has to have worldsheet 2,2 supersymmetry. So that's the setup that I'll be working with. And what we do is the most elementary thing one can do. We compute the BPS spectrum of the boundary theory or of the bulk theory, if you wish. So these all correspond to space-time. I mean, the boundary CFT operators that are chiral ring elements. So their dimension is determined by this U1R charge. And furthermore, once we do that, we will compute the next simplest thing, which is the structure constants of the chiral ring of these boundaries. And we do this not by computing correlators of the worldsheet CFT, but instead we use the operator product expansion of the worldsheet theory to derive the operator product expansion of space-time. So I mean, I've said lots of CFTs and lots of space-times and worldsheets. I hope the idea is clear. I have a 2,2 supersymmetric theory in ADS3 with compact spaces S1 and Y. This is supposedly dual to some holographic theory that lives on the boundary of ADS3, which has 2,2 supersymmetry, superconformal symmetry. And we want to construct the chiral ring of this boundary. And we do that by using this powerful Bezonian-Witten model that describes strings in ADS3. Okay, so the slogan is the space-time OP from the worldsheet OP. Are there any questions at this point? Or clarifications?
Sorry, Sujay, can I ask some?
Yeah.
So there are actually a class of examples. I mean, by taking dihedral orbifolds of T4, which leads to 2,2 SCFTs, and this can be identified with ADS3 cross S3 cross T4, and if you orbifold the S3 cross T4.
Yeah.
I mean, these also have like 2,2. This is some class of examples which were constructed by Matthias, Lawrence, and myself. So
whatever I'm about to say will apply to all 2,2 models, in my opinion.
I see.
It should, because I'm assuming nothing about the compact space. I'm saying all I require is an S1, and Y has to be, CY has to be 9 minus 6 by K. And I'm just saying, what is the most general thing one can say about such models? So it should include all the models. That
but the examples which we proposed, they didn't have an S1 like explicitly. I mean, so it was like ADS3 cross S3 cross T4, and then the S3 cross T4 is like, say, orbifolded by.
So one should be able to find an 2,2.
Right. Yes.
And I'm saying I can embed it like this.
Okay. Yeah. Okay. Yes.
Yeah. So I'm making no assumptions about what Y is at this point.
Okay.
Okay. So I should say that the structure constants for the 4,4 theories were of course known. They were derived a long time ago by the Butler, Pacman, and also Viribey, Pacman, and Vestelli, I think in 2007. So what we do in this work is to compute the structure constants, at least in the sector with no spectral flow, and show really how it depends upon the topological properties of this Y theory. And just to make contact with your previous talks in the conference, this is an example of what in Rajesh's talk was called the easy direction, to go from the world sheet to the space-time. I mean, he's talking about the much harder task of going from space-time to world sheet. So this is this is simpler in that respect. Okay, so let's give some details about the world sheet theory. So the world sheet theory, like I said, is an SL2R at level K times U1 current algebra times this superconformal theory with 2,2 on Y. The radius of the circle is set by the ADS scale. And what we first need to do is to understand how to describe these chiral ring elements from the world sheet theory point of view. So we had these boundary conformal dimension and boundary space-time R charges. So these just map to the following eigenvalues of the world sheet theory. So the J03 eigenvalue of the SL2R maps to this conformal dimension of the boundary theory, and left moving or right moving momentum along the S1 maps to the space-time R charge. So what we need to do is to classify operators based on these charges and just equate H and Q. Okay, so boundary chiral ring elements means that you are in the NS sector of the space-time theory. And these can arise from either Nevershots or Ramon sectors of the world sheet theory. This is the first point. So we start with the very general operator. We have some super ghost fields, bosonic ghost fields, some primary vessel 2R, some momentum mode along the S1, and some operator on Y that I don't know what it is at this moment. Now, the SL2R primaries and so on have been very well studied by Givian, Kotosawa, and Seiberg. So we construct, so we take from them the operator which has an ADS spin equal to small h. So the ADS spin h is precisely the space-time conformal dimension that we're looking for. So we fix that. And if you have fermionic excitations also on the SL2R directions, then this will be changed to h-1, or if you have Ramon fields, it can be h-1/2 and so on. But essentially, it is given by the h, the ADS3 spin. Okay. Then what we do is to demand that I have a chiral primary. So the momentum along the S1 should be equal to this ADS spin up to some proportionality factors. So if you choose an ADS3 spin H element from the SL2R, then you fix immediately the P left to be square root of 2 by K times H. Then we have to impose the fact that I have a physical propagating mode, physical propagating spring mode. So you have to set L0 equals half for the superstring or 1 for the bosonic for the matter part. And this will fix the dimension of the operator on Y, again in terms of the ADS3 spin. So what I'm trying to say is that the chiral ring is operator, the worldsheet operator that corresponds to a boundary chiral ring element is completely fixed by the ADS3 spin. And then one has to impose the GSO constraint, which means locality with respect to the space-time supercharges. And once we have this, we are almost there. There are two additional constraints. And the first constraint comes from study of strings in ADS3 by Marissa Naguri, which showed that the ADS3 spin for discrete states have to be bounded between half and K plus 1/2. And secondly, if you want a unitary theory on Y, then the dimension of this operator on Y has to be bounded by the central charge of the theory on Y. So there are two inequalities. And if you go through the details, what we showed is that the only way to get boundary chiral ring elements is if the operator on Y has to be either a chiral primary, I mean a worldsheet chiral primary, or a worldsheet anti-chiral primary, or a Ramon-Ramon ground state of the theory Y. Okay, so I mean, previous works have seen this for various cases, but without any assumptions, we have just shown that this is an if and only if statement. So this is one of the results of our work. So given all this, here is a list of operators at zero spectral flow, and we can also do this with spectral flow. There's no problem. So you can see that there are two types of operators in the NS sector of the worldsheet theory, and a different kind of operator from the Ramon sector. And this is the boundary conformal dimension of these operators. So the first step is done. We have obtained the BPS spectrum at zero spectrum. Okay. Any questions? Once you get the spectrum, then yeah. Was that a question?
No, you continue.
Okay. Sure. So what can we expect for the chiral ring? So the work on the chiral ring goes back to the classic paper by Ayan K, and Warner. So if you take a general operator product expansion of two fields in the boundary CFT, you will find something that looks like this. But because I have a chiral ring element, charge conservation of the U1R charge conservation ensures that the OPE or the operator product expansion is completely regular. So what we want to find is a C123. Another point that I'll come to at the end is the fact that the chiral ring has been shown to be topological by work by Cecotti and Waffa. So one expects these structure constants to be determined by the topological data of the worldsheet theory on Y. And for n=4 models, what people did was to compute physical 2 and 3 point functions and then take ratios to read off the chiral ring. So here what we're going to do is to directly the OPE from the worldsheet CFT. Okay. So one complication is the fact that because we have these picture numbers and so on in the superstring, we have to not just find these operators. So here I've written the operators in the canonical picture. So -1 in the NS sector and -1/2 in the Ramon sector. If you want to find the OPEs, then we also have to know these operators in the other pictures, in picture number 0 and also picture number -3/2. So this we can do. So for instance, one of these NS operators in the 0 picture looks like this. You know, it's some currents acting on these or some descendants of the fields in Y. So it's complicated, but it can be done. So once we have all this machinery in place, let's compute the OPEs. Now, the OPEs in the S1 direction, the fermionic direction, this goes, all of these are standard, you know, they're all found in textbooks by now. So the only non-trivial part is really the OPE in the ADS3. And the OPE in the ADS3 looks like the following. So this is from Teschner. I should have given a reference. I'm sorry about that. But again, once we impose the fact that I'm in a chiral ring, then it turns out that really the only OPE one need is completely trivial. So when the H3, when there's H on the right-hand side is the chiral ring element on the right, in all but one case of OPs that we will calculate, we'll get a trivial OP in the ADS3 sector as well. So really the only missing ingredient is a set of OPs in the Y sector. And this is something that we did from scratch because we couldn't find these OPs anywhere in the literature. But again, the idea is very simple. You start from the worldsheet chiral ring, which is just what I've shown here in this equation. And this is determined by the structure constants of the worldsheet theory on Y. I don't know what they are, but they are some R. Given this and given a spectral flow, which is guaranteed because of the 2,2 superconformal symmetry of the Y theory, we can determine all the others because the Ramon ground states and the anti-chiral primaries can all be obtained by spectral flow by half or 1 unit on the worldsheet. So for instance, I've just given you sample OPs for chiral ring and Ramon ground state or chiral ring with anti-chiral ring element with the anti-chiral ring element. You'll see that it's a bit complicated, but it's really quite simple at the end. So here, the coefficients now depends upon not just the chiral ring, but also on the homological metric, which is actually non-topological data. So it'll be one of the interesting things that we'll see is how, at the end of everything, the space-time chiral ring indeed depends only on topological data. So that's one thing to look out for. So now we also have the OPs in the Y sector. So how does one do an OPE? So again, this is textbook material. If you open the yellow book on conformal field theory, you'll see that if you have composite operators, you use the generalized Wick theory. So we have these operators where you have current times and primary OPE with a primary. So you just do it successively, and it's just standard OPE techniques. Okay. So now let's come to the only subtle point in the evaluation of the OPE. So what we get is the following. So because I have a 0 ghost operator in the NS sector, for instance, I have an integral over the insertion of one of the operators. Then the ADS3 OPE will lead to integral over these intermediate ADS3 spins. I have some worldsheet dependencies and all these operators here. And the boxed element is some differential operator that acts on this phi j element. This differential operator not simply on the worldsheet, only on spacetime. Now, what we find is that in the limit of the spacetime OPE, so now I take the limit that x1 goes to x2, where these are the two boundary points of my colliding fields. Then what we find is that the only contributing element, or the leading element, the leading term that contributes to this OPE fixes the ADS3 spin to be exactly that for a propagating mode. Okay. And once you set that in, all of these things essentially collapse to a chiral primary on the right-hand side. Okay, so I'll say this again, and this is a point that was made by Aharoni and Komorgotsky back in 2007 or 2009 maybe, where they were also trying to derive the spacetime OPE from the worldsheet OPE, and they found that in the spacetime OPE limit, the dominant contribution to this worldsheet integral arises from onshore states. So in the J integral, this essentially amounts to doing a residue calculations, and the result is a chiral primary at the end. Okay. So given all the NS sector and the Ramon sector fields from the worldsheet, we can do this for all possible OPs that can exist, and we can use the same trick of this worldsheet to spacetime OPE, and the answer is extremely simple. So what we find is that there is in all but one case, we get a universal coefficient that depends on the conformal dimension of the field on the right. So H3 is something like H1 plus H2 minus 1. And everything that appears on the right-hand side is purely topological. So it's either a structure constant of the worldsheet theory and Y, or it's what is called the topological metric by 𝗀𝗀𝗀𝗀 and Waffa. And to do this, what we did was a simple change of basis from what we did. So we redefined one of the operators. And once we did that, we see that all the OP coefficients is purely topological. So this is what one would expect naively, and this is what one finds. So whatever Y is, what we are saying that the OP coefficients looks exactly like this. Okay, now let me come to the only non-universal contribution to the OP. And this arises because of this ghost number business. So because of this zero ghost term, zero ghost operator, one of the contributing terms for one of the OPs involves a descendant of the primary on Y. So this is a non-universal contribution, and this we cannot know what it is unless we work out explicit models. So again, we went back to those two particular models that we had, the n equals 4,4 case, and this n equals 2 theory, which is a sum of 3 minimum models. So here Y is sum of 3 minimum models, and we try to evaluate what this OPE should be in that case. And we again find a surprise. What we find is that the structure constant is, the methods are the same. And now we find a non-trivial product of two OPE coefficients, one from the ADS3 factor and one from the SC2 factor. But again, because once you impose the chiral primary condition, what we find that it's again a constant. So in a way, it's disappointing. I'm not sure we understand what this means. And I'll discuss whether this implies a non-relation theorem or not at the end. It's not clear if such a cancellation occurs for all Y. It's highly unlikely, in my opinion. But for the universal class, for a large class of OPs, the result is indeed universal. Okay, I hope this point is clear. So now let me comment on the results. So one important point to make is that we did not compute the OPEs in the in the spectral flow non-zero sectors. Given that, so assuming that we can do that, suppose we set this combination H minus 1 plus KW to be some n, some integer n, then what we can check is that this coefficient 2H3 minus 1 in terms of this n becomes n1 plus n2 minus 1. Okay? And this is the same combinatorial structure constant that arises in the study of symmetric orbifold QFTs by Lunin and Mathur, where these NIs have the interpretation as these lengths of permutation cycles in the symmetric orbifold conformal field theory. Now, for the n equals 4 models, there is a non-renormalization theorem that has been proved by Debord et al. That shows that these structure constants of chiral ring operators are covariantly constant on the moduli space of this n equals 4,4 theory. So whether we compute it in the worldsheet theory or whether we compute this in the space-time theory, in the symmetric orbifold point, they should match. So for 4,4 theories, there's a non-renormalization theorem that makes full use of the full n equals 4 algebra. And so this match between this and the symmetric upper is not a surprise. But for us, it is a surprise because for n equals 2 theories, the structure constants do change. They satisfy these TT star type equations of Chekhov and ୱା𝗲. And it's not clear why we again find this, these combinatorial factors. And more surprisingly, for the two specific examples, well, for the one non-trivial n equals 2 examples that we studied, we again, for the non-universal factor, we find this n1 plus n2 minus 3 coefficient in that case, which again suggests that there should be some symmetric Amitabh interpretation, but why they should match under deformation to go from the symmetric Amitabh point to any other point is not clear to us. So this is gives rise to lots of questions. Will this hold for other models? We don't know. Does this imply or suggest some non-renormalization theorem for n equals 2 models? I don't know. But the only calculation that we can do indicates that there is some relation to a symmetric Amitabh dual. So with that, I'll stop and I'll take questions. Thank you.
Thanks, Sujay. Questions? If you can raise your hands, I can go one by one.
Yeah, I can't see the screen very well. So yeah, maybe it'll be good if you can tell me.
No, it's okay. I will coordinate. Souvik Dutta has some question. Can you unmute and talk? Yeah.
Yeah. Hi. So thanks for the nice talk. Just sorry. So actually, the examples which I was mentioning is for those dual CFTs which we had. Those were actually symmetric orbitfolds.
Okay.
Yeah. So usually for the 4,4, you have the symmetric orbifold of T4, or say that symmetric orbifold of K3. But for the 2,2 case, you take you orbifold the T4 first in some way, and then take the symmetric orbifold of that.
Okay.
So yeah. So I mean, probably there is some relation with with
yeah.
this.
For the 4,4 theory in our formulation. The Y theory is, for instance, T dual to a minimal model times T4. And the symmetric orbifold is just of the T4, not of the minimal model. So in the general case, it's not clear to me what exactly our symmetric orbifold, but it's a good question to think about. Yeah, I don't have an answer.
And also, can one say something generally about the elliptic genus of this of these theories?
Yeah, it's a good question. I don't have anything to say in the stock, but yes, one should be able to, I think. Yes. There are papers by Alejandra Castro and so on, I guess, who do.
Yeah, but for those cases, there wasn't a precise identification with the bulk dual. But since you have something more precise here, probably.
We have not tried to do that. But yeah, it's a good question. It's definitely worth it.
Thanks.
Anyone else? Okay, so I don't see any raised hand. I think Shauvik's hand is the old hand. Okay. Okay, so let's thank Sujay Ashok for this nice talk, and we will move on to the next speaker, Semanti Dutta.
Hi.
Yeah.
I'm sharing my screen.
Yeah, can you share the screen?
Can you see my screen?
Sorry, I think oh, yeah. So bulk gauge.
Okay. So am I audible properly, right?
Yeah. Yeah.
Okay.
So you're a postdoc or a?
I'm student, graduate student.
Yeah, you're a graduate student working with Bala Satyapalan.
Yeah.
Okay. Yeah.
Okay.
You can start now. You get about half an hour.
Okay. So hi everyone. Today's topic. My topic of the talk is bulk gauge field from boundary CFT using exact renormalization group. So this is a work done with Bala Satyapalan and Pavan Dharani Pragada. We all are from IMSC Chennai. So first I will motivate come to motivation part. So ADS-CFT correspondence gives a dual. Also suggests that the scale of boundary can be interpreted as time direction in the bulk. So although this ADS-CFT correspondence gives a definite conjecture like a partition function in two sides is equal, but still if one try to with some boundary conditions, if we want someone try to calculate the classical action, that means IR regularization, and that can be related to boundary RG transformation. So this nomenclature is called, comes under nomenclature of holographic RG. So it is useful to understand the precise connection between holographic RG and RG of boundary CFT. So can we obtain the holographic RG equation starting from the boundary RG equations without invoking ADS-CFT conjecture? If so, then it will give further insight into this correspondence. Okay, so with this motivation, I would like to point out to some literature of the holographic RGs. So first idea of holographic RG was given by E.T. Akhmedov in 1998, where classical equation of motion of Subra was, he told that can be interpreted as RG on SOIM side. Then there are a series of works after that. One is Bala Subramaniam Krauss in 1999, where they found gravity action with IR cutoff, and they also raised this question whether bulk equation and field equation can be obtained from CFT side. So then there is Boyer-Varlinde in 2000, where they also have written classical equation of motion in terms of Callan-Szymanski equation. They also pointed out a similarity between Hamilton-Jacobi and Polchinski equation. Then there is a series of papers of Sendries. So here I mentioned only one. So we have a lot of papers. Then Harrow, Sendries, and Solodukin in 2000, where they did IR regulation of an Olsen bulk action, and they calculated holographic stress energy tensor and the related conformal properties. So there is one important paper by Polchinski and Hemschirk in 2011, where they asked the question which radial cutoff in bulk correspond to boundary cutoff. And they also interpreted Wilson action, bulk Wilson action in terms of integral transformation of boundary action. Then there is a Faulkner Rangaman in 2011. They have interpreted Hamilton-Jacobi. They have found Hamilton-Jacobi equation for boundary and Wilson action. Then Lizana Morris and Victoria in 2016. They have found Wilson and RG on both sides, and they matched beta function, 3-point function, etc. Then Sansik Lee in 2010 and 11, he also derived a bulk dual from Wilsonian RG of matrix model. And Melo Santos in 2020 deriving bulk dual, applying local RG on BFSS model. And yesterday also we had a talk of Rajesh Gupta. He, with his collaborators, have done direct proof of equivalence of bulk string theory and boundary CFT in some cases. And there are many more works and there are several in these papers. Okay, so first I will start with the idea of holographic RG. To that, to understand that, it's best to look at ADS space in Poincare patch. So if you fix the Z, Z looks like a lattice spacing of the boundary theory. So one can speculate that change in Z is scale change of the boundary theory. And then in bulk, you can write, then another input is in bulk, you can write bulk action in terms of purely bulk term and one boundary term. Okay, so Z is equal to 0 is a boundary for Poincare patch, and this is a boundary term where epsilon tends to 0. And also in boundary, I effective is a Wilson action. We will see these things later. So this is effectively like we are changing the scale in the boundary and we are getting effective action. So what in holographic renovation, what people do is they interpret a interpret SP as a boundary state where 0 to epsilon z has been integrated out. So in this paper of Faulkner, Liu, Rangamani, they have shown that delta SP delta epsilon gives Hamiltonian of radial evolution. And also this gives a Hamilton-Jacobi equation in the bulk. So this is one kind of statement of holographic RG. So our statement will be on the other side. We will try to give a holographic RG statement from RG of the boundary. Okay. Okay, so that question I have written here, that can one obtain holographic RG equation directly starting from RG of the boundary theory. So it's better to tell it is holographic RG also, or one can take this is holographic form of ERG, something like that also. Important is we are not invoking any ADS-CFT conjecture. Okay, and in this purpose we choose exact renormalization group, because concept of scale is natural in this cube. Okay, now I will just brush up some ideas of ERG. So ERG is like renormalization group evolution is no more to be seen as in old days of removing infinities and by adding counter terms in Lagrangian. Rather, it is seen as a process of changing scale. It's a changing of scale from lambda1 to lambda2, wherein integrating out the higher energy modes. But whenever you are integrate out high energy modes, you pay a cost for that. So in the effective action, there will be a lot of irrelevant terms, like negative mass dimension terms will come. Like for example, in phi4 theory, in effective action, it will have phi8, phi10, or phi6, all kind of terms, whichever is consistent with the symmetry of the theory. So in ERG, what happens is why the name ERG comes, the suppressing of these high energy modes is done with analytic cutoff function. So for that, result of that is new correlator. What is the low energy correlator can always give back the old correlator. So that is no loss of information. In that sense, it is called exact. So these are the qualitative statements about ERG. So whatever I have told qualitatively, I will tell in this slide. Mathematically, we are considering a bare action. Okay, we are considering a bare action. You can see that this is the Gaussian term and this is interaction term. So you can see that we have choose K in such a way that if P is slightly greater than lambda, it dies out very fast. And if it is less than lambda naught, then it becomes 1. That means effectively this is a theory which is where all the momentum which is greater than lambda is suppressed out. So what people do is they just decompose phi in terms of phi L plus phi H, and you integrate out phi H, and then we can write a partition function in terms of effective action at phi L and at this function integral over the phi L, where this is the complicated action I was talking about. So this is given by this. So all the complicated part is contained in this direction, but this term, and this is the part you can see that now this has changed to k to the power p by lambda. So it's a theory of scale lambda now. Now the next question one people do is they find how is lambda is changing with a lambda. So T is defined as L in lambda, and that is given by Polchinski equation. Okay, that is given by the Polchinski equation, which is of this form. So take away from these slides will be, this is the form of in the last letter of the rest of the talk. So to derive vector, before we consider a simplest case, derivation of ADS-free scalar action from boundary CFT using ERG. So that is essentially a 3-step procedure. So write a Polchinski ERG equation for d-dimensional boundary theory, write evolution operator for ERG equation as a functional integral over a d plus 1-dimensional theory. So as you have seen, now we started with boundary theory. Now we have an extra thing, T, like L and lambda. So that will be our extra dimension here. And then okay. So from that evolution operator, we will do some field redefinition to map that d plus 1-dimensional field theory to our d plus 1-dimensional ADS space. So this is the three steps. These are the three steps we'll apply everywhere in the talk. Yeah. So now, okay. Now we will write. Okay. So suppose we consider this part of Gaussian action. So it is of this form. This is the Gaussian part, and this SI is the perturbation. And then Polchinski equation, one can write in this form. So here we want to comment one thing. So Polchinski equation or ERG equation, better we tell. If it will depend on the form of SI. If it will change on there will be extra term if you consider different kind of SI. But if you choose SI, just means if your Polchinski equation is of this form for SI, then it should give you the ADS free action. Okay, now we will see that if you look at this equation, it looks like a Schrodinger equation. So you can find the evolution operator for this equation. So that is given by this expression. And then using the usual functional integral thing, you can write psi pi I ti in terms of phi ftf, where phi n and ti are the boundary conditions, and we are summing over all initial conditions. So this is important step for us. This we can tell that this is a holographic form of ERG. Like we told that how SB is changing with respect to epsilon. That is given by Hamilton-Jacobi equation. So those are all bulk statements. Here we are giving an equivalent statement of holographic ERG, but everything has run from the boundary theory. But and also we can detect this as Hamilton of radial evolution, which will be a d plus 1 d. Field theory. So, but that okay. Yeah. So step 3 will be consider this radial evolution action, and you do following 3 things. One is do this field redefinition, then do this change of variables, and choose AF to satisfy following constant. If we do this, we get a free scalar radius action. Okay, now how to change the M? We are choose the M. We are coming to next slide. It's like if you see that we are defining F in F has a relation with G dot, and G is a Green's function of the theory, which is known to us. We are starting with, suppose for boundary current, we know what is the G for that theory in low energy limit. So using that, we will determine M square. How? Like it is like first one can see that the bulk field. So Y is we are like phi is the boundary field. So Y is we are interpreting as bulk field. Now the equation of motion of the bulk field and 1 by F satisfies some equation. Also, most importantly, the form of 1 by F is given by linear superposition of these Bessel functions, where nu square is m square plus d square by 4. Now I told that F is related to the Green's function. So from that you can find the nu. What is the nu in the low energy limit? So from that you can find n square, and that n square should match with whatever radius CFT correspondence predicts. And also once you have ADS action, then correlators also can be calculated in standard. So these are the procedure one will do to get it. Okay, so if there is no question, then next what we will do is we will derive gauge motion in eddies. So for that, that 3-step procedure is always will come there. But before that, there is a problem that how to construct the action of a boundary current. So first we state the key points and result that boundary conserved current is expected to get mapped to gauge field in bulk. So to do this, first we have to do, there will be a concept of auxiliary field, which I will come in later part. We have to find the action of a boundary current using that concept, and we have to find ERG equation for the Wilson action of that auxiliary field.
Semanti?
Yes.
Your voice suddenly breaks for few, a second or so sometimes. So it's not clear whether you're off the microphone or you're just make conscious effort and continue your talk. Yeah.
Okay, so is it better now?
Now it's fine. Always it's fine. Just for a second, sometimes you're off the microphone and then it continues. Yeah. Now
maybe
you're
close
fine.
the video and try again. Maybe it might be just close the video for bandwidth.
Oh, okay. Video. Yeah.
I mean, close the video and then try again.
Yeah. Okay, now I think it will be better.
Yeah.
Okay. So I'll state the key points and result. So one thing is the mapping to ADS procedure is same as pre-scalar case, except now there will be d number of scalars because there is d number of boundary currents, and there will be one extra field redefinition because of presence of space-time index. So specifically what we will derive is, which is done in Kabat et al. In paper of 2012, it's a scalar field equation or d number of scalar field equation with mass m square 1 by d, which is consistent with ADS safety. We will derive this equation. So from this equation, if someone does phi is equal to z a mu, one recovers source free Maxwell's equation. This is our aim. But for that, first we have to construct the action for boundary current. So first we will see that how to not deal with a current operator in order to map to ADS space. So what one can do is, in usual sense, is that a partition function we can partner with this star, where J mu is the bulk current and M mu is the source. Now as we flow to low energy, so usually in ERG, the concept of composite operator is defined by linearized perturbation. Like you start with this bare action, you flow to low energy, integrate out or high energy modes. And then whatever is remaining, which is proportional to mu, that is your low energy version of the action, of the composite of the operator, bare operator. But this is not very useful. This is not useful in calculating bare correlator, because if there is a single insertion, then correlator at S lambda is equal to correlator at S beta. But if there is double or more relation, these correlators are not equal. So other dots are fundamental fields. Okay, but we would like to get back original bare correlator in the boundary at any point of time. So we are starting with the CFT theory, which is at boundary, and we are always interested in the boundary correlator. So even though we are integrating out, going to effective action, integrating out high energy modes, but we will always like to find the boundary correlators. So that's why these quantities are not useful for our purpose. So for that, what we will do is we will introduce auxiliary variable. So it is well-known thing that people in large and expansion to do with this auxiliary field. So definition is it's a dynamical field, but there is no kinetic energy at free level. But if you go to lower energy field, lower energy action, there can be kinetic energy term. Okay, so Z mu is now written as, so sigma and chi is our auxiliary variable. So here, how we have done it is that the original action is same as that, and we have put a delta function here. So chi is that variable coming from delta function, and sigma we have put at is equal to boundary current. So if we do that, then one can show Z mu is related to S sigma. You can see this is related to S sigma. This looks like a Fourier transform of A mu. That means it's somehow related to, you can either map A mu to the bulk or sigma mu to the bulk. Okay. It's somehow related to the standard or alternate quantization in ADS-CFT. And where S sigma mu is defined by this equation. So from this definition, if one find a correlator of sigma sigma, one can always find it is equal to the J mu. So J mu is the correlator, bare correlator, that is always equal to this Bayer correlator at Bayer theory. So that means we can always get, whenever we find the correlator of sigma sigma, we can always get back the boundary correlator.
Voice is not heard
correlators
now.
in the Bayer. Okay.
Yeah, now I can hear. It's
okay.
Probably you're shifting your microphones when you're speaking. In a few seconds we don't hear. Yeah, continue.
Okay, please tell me when it is not.
Yeah, now we can hear you. Yeah, continue.
Okay. So so S sigma mu, e to the power A sigma mu. With that, we can always find correlators of sigma from which is always equal to J mu of S Bayer action. But still, J mu is not correct definition of current all over the scale. So this is a current definition which is satisfies conservation laws in Bayer theory, not in low energy theories. So sigma mu should be chosen in such a way that it satisfies conservation law at all scales. So that's why we are going to set up to define the effective current. To do that, first we do is we define the external gauge field A mu to gauge the ON symmetry. So where these derivatives are defined in terms of external gauge field, and then define current in this with this definition. So here you can see that as we choose in this definition J mu, and if whenever you do n number of differentiation, you will get n correlators of J mu. So this gauge impedance of ZA mu and this definition ensures that sigma mu satisfy conservation law all the time, means all the scale. So we take definition of auxiliary variable as this definition. So we know what is Z mu and we will apply this delta function. Okay, so so this is relation among Z mu. Okay. So now our next work will be that what will be the Polchinski equation for ON model. So we are considering ON model, although it is free, but there are a number of fields. So one thing is always conservation law of sigma mu is there and J mu is gauge invariant. So we choose some gauge del mu n mu 0. And sigma mu is a variable of our choice. So all the variables we can choose as transverse. So we want to map, what we want to map, instead of A mu, we want to map sigma mu to the gauge field in the level of kinetic time. Okay, so for that purpose, we don't need A mu. So we can put A mu 0 and we can find ERG equation for S lambda sigma. So if someone can, okay, it can be shown that Polchinski equation for S lambda sigma mu is given by this, where phi L is there, phi h has been integrated up to scale lambda, and sigma mu is like an external field. Like if you see the definition of sigma mu, yeah, so this is like a it's like an external field with respect to chi. So if one okay, so there
you have about 5 minutes. I hope you are.
Yeah, okay. So if we got this Polchinski equation, then we are done. But one thing is we will evaluate it with phi L is equal to 0 for simplicity, because we want a term like sigma mu dot. We don't want anything with respect to phi L. So if we find this is e to the power A lambda quadratic terms in chi mu, and first order, then field with respect to chi mu. So we replace chi mu with respect to as a delta of delta sigma. So we get the ERG equation in momentum space as this. So this is our ERG equation of S lambda sigma mu. And these variables are also in terms of sigma mu. So this form of I mu is not, while mapping to kinetic energy, it is not important. It is related to vacuum polarization diagrams of QAT. but that will come only when you try to calculate correlation function. So the leading order solution is given by this. And most importantly, what we want is holographic ERG equation for boundary current is given by this equation. So now F square is kind of, okay, so this is our radial evolution action. And we will work with this action. We will show that by mapping, you can map it to the gauge field. So this is our starting point. This is the equation. And here now it is F square is a little bit complicated than previous scalar case. But we do the same three-step procedure and we get equation like this, which is free scalar equation, but now number of scalar is d, and we have to determine the mass. So from the constant 1 by f, we have told it's a linear superposition of Bessel functions. But again, if we know this theories of boundary current, we know what will be the g. So we can determine the nu, and from there it can be shown m square is 1 by d. So this is our scalar. So if you find the equation of motion, this is our scalar equation of equation of scalar field with m square is equal to 1 by d. And if you do the another field redefinition, as I mentioned before, z of z into one new field, then you will get back a source Maxwell's equation. So this all I have to say about the topic. Then I just want to make a comment on bulk graviton. The same method applies for mapping of conserved EM tensor to gauge fixed bulk graviton action. So for that, what happens is in boundary, one use conservation and tracelessness of EM tensor, and in bulk, AZM is 0, and diffeomorphism invariance and tracelessness of gravity. So with these things, one can see that one is expected to get a graviton equation from in the bulk. So here also one can define an auxiliary variable sigma mu, and in the same way they can map the radial action to equation of scalar fields. There each of them will have mass 0. Okay, so on that note, so this is end of my talk. So I can say whatever work can be done after this is immediate work is to extend to interactions in case of graviton and gauge field. So equivalent work has been done for scalar composite operator phi square in phi-4 theory ON model. By Balasatyapalan in 2020, where in next order, where it has been shown that polycyclic equation have some next order terms also, which will have a form of cubic potential term, and that we can map it to ADS space, and we can show that gives expected correlators according to ADS CFT. So after we do maybe this same analysis for boundary current and EM tensor, one can try to make connection of the above results with Vasilev's theory. And it is also interesting to see how bulk locality arises, because whatever formalism we are doing everything from the boundary. There is everything from the boundary. We are doing ERG from the boundary, and but we are getting an action, but we don't know whether that action will have locality or it will be a really bulk dual, whatever ADS-CFT predicts. So that is an interesting question. So these are the questions we will visit in future soon. Okay. On that note, I'll end my talk. Thank you. Question, comments.
Thank you, Semanti. I think we are running late. Maybe we'll take one or two quick questions, and then I'll hand over to Arnab Kundu has a question.
Hi, I have a very quick question, and I missed the first few minutes of the talk, so maybe I'm confused about the notation. So my question was the ERG equations that you wrote. You had on the left-hand side, you had a derivative, right? The first order derivative. And this T was exactly what? Was it log of energy scale?
T was log of lambda.
A log of lambda, and on the right hand side you had this capital lambda, which is the cutoff, right? So in this
Yes,
formalism, is there a natural way to say how low can lambda be?
No, it it can go up to 0. Lambda can go up to 0.
Okay.
So,
okay.
but if you go to lambda tends to 0, there will be higher divergences. So that did
And
it mean that
that divergence has a particular
in the
behavior
bulk
with
theory,
lambda?
like if you go to lambda tends to 0, and
Yes.
if you map to ADS bulk action, then there will be higher divergences. Which appear in usual ADS case also.
Okay, and that goes with the power of lambda?
Okay, we haven't studied that thing, yeah, so
Okay.
I cannot tell.
Okay, thanks.
Gautam?
Yeah, hi Semanti, thanks for the nice talk. I just have a general question, and the specific questions I can take later on offline. So the general question is that you said that you were doing this without using ADS-CFT.
Yes.
But what? So this particular point, aren't you using something like GKPW at any stage, or the relation between the cutoff field theory and the ADS theory with some particular radial cutoff? Even that is not used. I mean, what is meant by not
we are
using
just
ADS-CFT?
No, we are just using the ERG equation, and thus this is, you can see this is just Polchinski equation, and then you are just essentially what we want is the evolution operator. That's all we are using, and this is a functional integral result. And
I can see the. I mean, I didn't completely follow the formalism, but I'm saying that aren't you making an identification between the ADS radial cutoff and the field theory cutoff at any stage?
so ADS radial cutoff means if you tell Z is sort of 1 by lambda here, maybe in that sense you can tell that lambda is low energy, that scale in the boundary, and
so that is one of the essential inputs from ADS-CFT. I mean that if you look at the papers of
it is motivated by ADS-CFT, but these all things are mathematical. You can make this change of scale. So you are not using. We are motivated by ADS-CFT, but we are not using any input from there.
Okay, all right. Yeah. Okay, thank you. We can continue the discussion later on. I mean, I'm interested in knowing a little more. Thanks a lot.
Okay.
Bye.
Okay.
So with running late in the session, I think let's conclude this pre-lunch session, and I'll give it to the organizer Alok to take over. What will be the lunch break? The tea break.
Again, I'm going to request a cut down on the tea break to down to 15 minutes. So is it okay if we reconvene 15 minutes from now, 11:30 sharp? Is that okay?
Yeah, that's fine.
Chandrashri, are you there? Hey, Chandra, are you there? I think he's the next chair. Hopefully he would join in. He knows that he has to chair. He was there in the morning. So let's reconvene in 15 minutes, 11:30.
11:30.
Yeah, so we have a 15-minute tea break, and I apologize. Even though the team had already sent me a link for that option, which Arnab Rudra had suggested, but we could not explore that further. So just give us till tomorrow. We will get back to you on that option of interestingly spending the 15 minutes tea break now. Yeah. So let's meet at 11:30, all of us, please. Everyone is welcome to continue with this link. We are going to be following a single link, a Zoom link for the pre-lunch, and a different but a single Zoom link for all post-lunch sessions. So let's reconvene at 11:30 sharp. Thank you.
Thank you.
Thanks, Rama.
Yeah.
Chandra, are you here?
Yeah, morning.
Good morning, good morning.
So we'll start in a couple of minutes.
Yeah. Can you see my screen?
Yes. So Alok, should we start?
Yes, please. Absolutely.
Okay, so welcome everyone for the post-tea session. So we have 5 talks here. And the first talk is by Professor Amitabh Virmani from CMI, Chennai. So Amitabh, over to you.
Okay, thanks. Can you hear me?
Yes, yes.
Okay. Yeah, I did not know whether I am muted or not. Okay, so yeah, let me start by thanking the organizers for putting together this conference and inviting me to speak. I will be talking about black hole hair removal for n equal to 4 CHL models. I will explain the phrase CHL models as I go along. Okay, so this is based on this paper that we put out last year and some work in progress. Okay, so here is the outline of my talk. I will give a broad introduction, motivation for our work, and a brief review of the papers our work is based on. Then I will present the supergravity analysis that we have done in order to construct these hairs. And these here we have constructed to resolve a puzzle for the CHL model. So I will give a statement about the puzzle of this hair removal puzzle for the CHL model, then the resolution that we have proposed. And then I will end with the summary and future directions. Okay, so let me start with the, so before I start, let me just make 2 comments. So this project grew out of Chennai Strings meeting in 2018. And this is based on a paper that we have done with 𝗬𝗵𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀 Gukova and CMI student 𝗦𝗵𝗶𝗶. Almost all the calculations were done by 𝗦𝗵𝗶𝗶, so she worked very hard in this project. And there is a concurrent paper by Aradhita and Justin David with the main result the same. Okay, so let's start. So black hole here, John Wheeler famously made the statement that black holes have no hair. And this statement has been made more precise over the years in what are called no-hair theorems. So these theorems say that in the presence of no matter other than the Maxwell field, the black hole is completely described by mass, electric charge, and the spin. Even if you add matter, some version of these theorems continue to hold, provided the matter is not very exotic. If you add exotic matters, then of course the theorems change. In particular, for more complicated setups, such as setups involving Kaluza-Klein dimensions, form fields, all these things will feature in my talk. Black holes here are possible, and we would like to construct such here. So in our context, black hole here is defined as a smooth, normalizable, bosonic or fermionic degree of freedom that lives entirely outside the horizon. Okay, so the phrase black hole here itself has several meanings in the literature. In our case, it is normalizable, goes to zero at infinity. Is it smooth at the horizon, and also goes to zero at the horizon. So it lives completely outside the horizon. There are many methods to construct black hole here. It's a big subject in general relativity. Okay, so why are we interested in black hole here? So our reason for being interested in black hole here is the relation between black hole here and the microscopic counting. So black hole entropy is in terms of black hole entropy in terms of microscopic degrees of freedom is insensitive to the nature of solution far away from the horizon. So if two black holes have identical near horizon geometries, they have the same degeneracy because they have the same near horizon geometry. And there is a apparent, at the same time, well-studied counterexample of this. This is BMPV black hole in flat space and BMPV black hole in top-net space. So there is a proposed resolution to this discrepancy in some sense, and the resolution goes under the name of hair removal. And this was proposed by these authors, Banerjee, Navamita Banerjee, Mandal and Sen, and Jatkar, Sen and Srivastava in 2009. So motivated by this, our work is hair removal for the CHL models. Okay, so I will not be able to go into the full details of our project. I mean, it has several elements, but I will give here a two-line summary of what we have done. So in 2009 papers, these authors did not treat the rotation of the black hole in sufficient detail. In our paper, we have put in a lot of computational effort to fill in this gap, but this is not at all the topic that I will be discussing in this talk. And also, in these 2009 papers, the authors looked at the simplest model. We look for a wider class of n equal to 4 models. And as you know, the generalization from K3 compactification to CHL models is sufficiently non-trivial. We will see that this hair removal story is non-trivial. Okay, so let me just say what are the models of interest. So we will be interested in models with n equal to 4 supersymmetry. And these models provide a rich arena for such discussion. For a class of CHL models, black holes can be described in terms of 6-dimensional 2,0 supergravity coupled to n-t number of tensor multiplets. Okay, so what we will do is that we will start by looking at black holes and the hair to these black holes in these theories. Okay, this is what we will start with. Okay, and then the aim will be to construct a black hole here in this setup. Now, it turns out that discussing all possible here is hard, perhaps not even useful. Matching of the microscopic indices of 4D and 5D black hole may be possible with the knowledge of few here. And this is the attitude that we will take. What we will do is that for the 2 black holes, we will study only 3 types of hair. And we will see that once we take into account these here, we will be able to explain the difference between the 4D and 5D microscopic indices. Okay, so specifically the modes we will be looking at are the so-called Garfinkel-Vachaspati modes. 𝗰𝗵𝗶𝗶𝗿 here. Then using the tensor multiplates, we will be constructing form field here. They all come from the tensor multiplate sector, and we will be looking at the fermionic here also. Okay, so this is the one slide summary of the work of 2009 papers of Sen et al. So on the left hand side is BMPV black hole in flat space. On the right hand side is the same black hole embedded in TOPNet space. So in TOPNet space, it admits here, and the aim of our project is to construct these hairs for these 4 general class of models. And once we construct these models, and then once we construct here for these models, we will see that the 5D partition function is same as the 4D partition function after removing the hair partition function. So 4D divided by the hair will give us the 5D partition function. Okay, so this is the picture to keep in mind, that we will be interested in constructing these wavy lines which account for the hair and which account for the difference between the two. Okay, so with this brief introduction, motivation, and review, now let me present the supergravity analysis that we have done to this end. So as I said, we will be interested, at least to begin with, we will be interested in 6-dimensional 2,0 supergravity coupled to NT number of tensor multiplates. So this supergravity theory is sufficiently complicated. It has many fields. In the bosonic sector, it has metric, self-dual, and anti-self-dual 2-form fields, and lots of scalars. In the fermionic sector, it has gravitinos and lots of Majorana fermions. So both for the solutions and for the hair, what we will do is that we will only consider setups where scalars are set to constant values. Okay, and all the spin half fermions are set to 0. This is the setup in which we will be interested in constructing the hair. So this is sufficiently simple and manageable. And we will only be looking for solutions, hair solutions, which preserve 4 of the 16 supersymmetries. Same supersymmetries as that of the black hole. Okay, so so BMPV black hole. So as I said earlier, in our paper, a lot of effort has gone into rotating BMPV black hole. But in this talk, I cannot discuss those details. So I will focus on the non-rotating BMPV black hole. So 5-dimensional BMPV black hole lifted to 6 dimensions becomes a black string. And the string is in the x5 direction. There are four flat directions. So these 4 flat directions are DWI, DWI, and U and V are the null coordinates in this geometry, which capture the time and the black string direction x5. The 4-dimensional BMPV black hole is obtained by embedding the BMPV black hole in TOPNet space. And what that means is that we replace the 4-dimensional flat space metric with the TOPNet metric. Okay, so these are the standard coordinates for the TOPNet metric, where chi-r is this function which goes as 1/r, and there is a constant here which determines the size of the S1 at infinity. Okay, so this function psi that enters here is also 1/r, but this r is the radial coordinate which is in the TOPNet geometry. Okay, this r is not the radial coordinate constructed out of these wi's. Okay, I mean, if you are familiar with the 5-dimensional black holes, you might say that it will be like 1/r squared, the harmonic function. But here I'm using a slightly different radial coordinate, and this radial coordinate is related to this TOPNet r, and here it goes like 1/r. Okay, so these 2 black holes have identical near horizon geometry. And what I will be doing is that I will be interested in constructing hair on these black holes. Okay, so what I will describe is the hair that we have constructed on these black holes. So the way I have organized this, I will first discuss the bosonic 5D hair, then fermionic 5D hair, bosonic 4D hair, fermionic 4D hair. So this is how these slides are organized. So let us start with the bosonic 5D hair. So bosonic 5D hair or hair candidates, they are constructed using the Garfinkel-Vachaspati transform. So Garfinkel-Vachaspati transform is a solution generating technique which maps a known solution to a new exact solution. And what this technique requires is a null hypersurface orthogonal killing vector. Okay, so satisfying all these three properties is not completely trivial. Few solutions satisfy all these properties, so that's why the Garfinkel-Vachaspati technique is not very widely applicable. But in our case, for the BMPV black hole in top nut as well as BMPV black hole in flat space, the technique is applicable. Both these black holes admit null hypersurface orthogonal killing vectors. Partial U is the vector that we will be using for this. So given that vector, we will do the transformation. The Garfinkel-Vachaspati transformation is new solution G prime is G plus T times KM. Okay, where KM is this killing vector. K upper M is del by del U, and you just have to lower the indices. Okay, so where this T is the scalar field which satisfied box T equal to 0, and it is compatible with the killing vector. Okay, so this was my one slide summary of the bosonic 5D here. For the fermionic 5D here, we solved the fermionic sector equations of motion and obtained the deformation in the gravitino. And we will work, to begin with, we will work with the undeformed background. We will find the hair mode, and then we can go and check whether the deformed background also admits the same hair modes or not. Okay. So this is how we have organized our paper also. So first we find the fermionic hair mode for the undeformed background, and then we check whether that hair mode is also a valid hair mode with the GB deformation. So for the fermionic sector, gravitino with only V component is taken to be non-zero, and even the V component is taken to be independent of U, in spirit with the fact that it should be compatible with the killing symmetry. And we find a hair mode in this psi alpha V. Okay, so now for the bosonic 4D, we again use the Garfinkel-Vachaspati method to find a class of hair modes. But now, because we have the top nut space, a new class of modes are possible, and these are coming from the tensor multiplate sector. And there are NT number of such modes that come. Specifically, the way it happens is that the top nut space has a harmonics 2 form, harmonic self-dual 2 form omega Tn, and taking the wedge product of omega Tn with dV, we can construct a deformation which belongs to the tensor multiplate sector, and this gives rise to NT number of hair. Okay, and in the same way we do the fermionic 4D. We find a solution that is independent of U for the V component, and we solve the same set of equation in the top nut background. It turns out that the top nut space does not have any effect on the fermionic deformation at all. Exactly the same equations, literally exactly the same equations go through, and we find the same hair modes. Okay, so now all these modes that we have constructed, now we have to check whether they are valid hair modes or not. And for this, we have to do 3 things. We have to check whether the modes are smooth or not, smooth near the horizon. And the way we will do this is that we introduce suitable coordinates which are smooth across the horizon and check whether the modes are smooth in those coordinates. The next thing we have to check is whether the modes preserve the right amount of supersymmetry or not. So in particular, no additional supersymmetry should be broken. And for this, we have to do the killing spinner analysis with the deformation added. And the next thing we should check is that the modes are only supported outside the horizon. This was our definition of the here. So all of these smooth deformations should vanish at the horizon. So once a mode satisfies all these three things, we will say that such a mode is a proper here mode. Okay, so when we do these calculations, we find that all the modes for the 5D black hole that we have constructed, they are supported outside the horizon, but the 𝗰𝗶𝗶𝗶𝗶 modes, they are not smooth across the horizon, so they should not be counted as here. For the fermionic modes, we find there are 4 here modes. For the 4D black holes, we find there are 3 𝗰𝗶𝗶𝗶𝗶 modes, which should be counted as here. So that's why I have written them in green color, and they are parameterized by these functions GIV. And for the fermions, exactly the same analysis apply. There is no difference. So we again find the four modes. From the tensor multiplet sector, each tensor multiplet gives rise to 1 here mode. So we find NT number of here modes. Okay, so here is the summary. So we have done explicit construction of here modes for the 4D and 5D black holes. These are nonlinear solutions. I mean, all nonlinearities are taken into account. And this is the spectrum that we have found. So for the bosonic, we find that there are no here mode on the 5D black hole, but for the 4D, there are NT plus 3 number of here modes. And for the fermionic sector, both of them have the same number of here modes. Okay, so questions, comments on whatever I have said so far? Okay, so now let me state the hair removal puzzle for the CHL model. So these 𝗰𝗶𝗶𝗶𝗶 modes and so on, these things I have been working on for several years. And in 2018, at the Chennai strings meetings, I was giving a talk on construction of some here modes for a different setup. And then Suresh commented that the here partition functions are closely related to the 𝗰𝗶PPS partition function. Again, this is something I did not know at that time. And from there, this collaboration started, and we started exploring how these here modes that we are talking about are related to the CHL models and the 𝗰𝗶PPS partition function. Okay, so it turns out that for the K3 compactification, the 𝗰𝗶PPS partition function, same as the here partition function, is eta rho 1 over eta rho to the 24. And if we think in terms of these languages, this language, then this is essentially what Sen et al. Had done in 2009. They explained this eta rho to the 24 from a here analysis. And the way this works is that for K3 compactification, there are 21 tensors. Tensor multiplets one gets in 6 dimensions. And if we go back and look at this NT plus 3, this is what gives rise to the 24 extra bosonic modes, and this is what enters in this eta rho to the 24. So, so the extra bosonic here modes is what explains the difference between 4D and 5D partition functions for the K3 compactification. Okay, for the CHL models, things are a little bit more subtle. So let me first say what these CHL models are. So the CHL stands for Chaudhary, Hockney, and Likin. These are some sort of orbifold models. The key feature of these models is that they have smaller number of vectors, say in 4D, or from the 6D point of view, they have smaller number of tensor multiplets, not 21, but smaller number of tensor multiplets. And then the K3 compactification. And these models are obtained by Zn orbifolds of certain Zn orbifolds of K3 times S1 times S1 tilde. The orbifold group acts as an X on the element of the cohomology of K3 on the self-dual and anti-self-dual harmonic forms. And it also involves a shift along the S1 direction. Okay, so now let us ask how many hair modes we are able to construct and what is the expected hair partition function. So, well, natural place to start would be the 6D supergravity description, because this is the description in which we know how to construct the hair modes. So this is what we did. So we obtained the lower dimensional, 6-dimensional supergravity description of these models. And then we just constructed the hair modes for the G invariant fields. So let's say for the Z4 CHL model, the number of tensor multiplates is 7. So what we have is NT plus 3, that is 10 extra bosonic hair modes. But how do we obtain the hair partition function, which is the 𝗰𝗵𝗶𝗶ci partition function, this slightly complicated object? You see, it has a lot of feature and there is no obvious relation to the number of G invariant hair modes that we are able to construct. Okay, so the resolution. So the resolution of this puzzle lies in thinking about the hair modes in 10 dimensions. So let us schematically denote Y to be the K3 directions and X to be the remaining 6 dimensions which we have used so far. Then in 10D, the Riemann-Riemann form fields schematically decompose as C4 is like C2 wedge omega. Okay, where omega are the self-dual and anti-self-dual harmonic forms on K3, and C2 are the fields. I mean, if you restrict yourself to G invariant modes, then C2 are the tensor multiplates that you will see in 6 dimensions. So on the elements of the K3 cohomology on the harmonic and on the self-dual and anti-self-dual harmonic forms, the orbifold group will act. So let's consider the Z2 CHL model, and let's try to understand this for the Z2 case, that is the simplest. So in this case, the orbifold group of order 2 will act on these quantities. So the way it will act is that there will be 8 anti-self-dual harmonic form omega gamma that will have eigenvalues -1 under the Z2 action. So out of these 19 anti-self-dual form, 8 will have -1 eigenvalues and 11 will have +1 eigenvalues. So this is for the C4, but then there is a similar story for the 2-form B field and all of those things. Okay, so if one takes all of that into account, then one finds that there are 13 tensor multiplates for the Z2 model, and as a result, NT plus 3, so there are 16 extra bosonic modes from the G invariant sector. And now there are 8 self-dual harmonic forms which have eigenvalue -1. So there are 8 modes which 8 hair modes which can be constructed with boundary conditions along the orbifolded S1, such that when you shift, I mean, that is the CHL action, under the CHL action, the C2 comes back to itself with a minus sign. Okay, so omega gamma has eigenvalue -1, and C2 under the CHL action also comes back to itself with a minus sign. Okay, so as a result, we have 16 bosonic hair modes with periodic boundary condition and 8 bosonic hair modes with antiperiodic boundary condition. And in correct quantization of charges, the periodic modes contribute even units of momentum along the S1, and the antiperiodic modes contribute odd units of momentum. So if we take this into account, can you hear me, Chandra?
Yes, briefly I could not hear. Now I can hear.
Oh yeah, actually the power just went. So okay, so so for the Z2 CHL model, the way this works is that so there are 16 periodic modes, so 16 even units of momentum modes. So Q, they contribute Q to the 2, Q to the 4, and so on. And then there are 8 antiperiodic modes, so they contribute odd units of momentum. And taking both of these Hare modes into account, we indeed get the half BPS partition function to be the Hare partition function. Okay, there are some more details, but the essential idea is as above. We indeed get the Hare partition function to be the half BPS partition function. Okay, so let me just end my talk with the Z4 CHL model example. So in this case, as I was saying earlier, there are 7 tensor multiplets. So there are 10 modes with the no twist. And then one looks at this Chaudhary law paper and figure out how many 2 pi I over 4 twist modes and so on. So in this model, there are 4 modes with 2 pi I over 4 twist, 6 modes with 2 times 2 pi I over 4 twist, and 4 modes with 3 times 2 pi I over 4 twist. So when one takes all of this into account, this is how the counting goes. So for momentum modes, which are quantized in units of 4, we have 10 such modes, 10 such here. So we get for 4, 8, 12, and so on, we get 10. For 2 pi I over 4 twist, we get 4 modes. And for these twist, we get 6. And for the other ones, we get 4. So when one takes all this properly into account, we indeed get eta to the 4, eta 2 rho squared, eta 4 rho to the 4. I mean, you can see this like 1, 2, 3, 4, like these come with the power 4. And then some powers are left here, and those combine into this and this. Okay, so we indeed get the Hare partition function to be the half BPS partition function. And this is all I wanted to say. Let me just end with the summary and future direction. So for the CHL model, the puzzle of 4D versus 5D index mismatch is slightly more challenging due to the presence of twisted sectors. And in our project, we have identified Hare modes in the untwisted as well as twisted sector. We show that after removing the contributions of the Hare modes from the microscopic partition function, the 4D and 5D horizon partition functions agree. Although I did not discuss this in this talk, but special care is taken in our paper to present details on the smoothness analysis of Hare modes for the rotating black hole. And this is really the main calculation that we have, a lot of calculations we have done in this regard in our paper, and thereby filling an essential gap in the literature. So this is work in progress. So now we are looking at twisted twining partition functions. So using the ideas which are central to the CHL model, one can define a richer class of partition functions. So these are called twisted twining partition functions. It was done by Ashok Sen and Suresh Govindarajan in 2010. The counting is known for these objects, and a similar Hare removal calculation needs to be done for these cases. And we think that we have understood most of this story. We are coming together to write the paper. So this is work in progress with Abhishek Chaudhary from IIT Bhubaneswar, Sutapa, 𝗬𝗏𝗶𝗶, and Suresh. Okay, that's all. Thank you.
So thanks, Amitabh, for a very nice summary. Questions, please?
Yeah, I had a question, if I can.
Yes, please.
So Amitabh, just is very nice work, looks like. Is there an analog in 3 dimensions, like with supersymmetric BTZ black holes or something?
The extremal BTZ black hole is supersymmetric.
I mean, only if you have a supersymmetric theory.
Yeah, in a supersymmetric theory, yeah. But whether this Hare removal analysis can be done for such a setup, this I am not aware of.
I mean, it should be doable, right? It can't be harder than 4D and 5D.
Yeah, no, I mean.
Or is it trivial? I mean, the only possibility is that there is no Hare for some reason.
No, I mean, there might be Hare, but what will you compare? I mean, so here the puzzle was that for the BMPV black hole in flat space and BMPV black hole in top net space, the indices were different.
Okay.
Yeah, so in that case, I don't know what would be the corresponding statement.
So you have to find the microscopic. So what is known about the microscopic index for the supersymmetric BTZ? Is it known beyond the leading term?
I would think so. I would think so. Yeah.
Okay. Thanks.
Yeah.
So any other questions? Okay, so if not, let's thank Amitabh.
Okay, thanks.
Our next speaker is Rajesh.
Hi, can you hear me?
Yeah.
Okay, so let me share my screen. Can you see my screen?
Yes, yes.
Okay, that's good. Okay, yeah.
So Rajesh will speak about some aspects of non-relativistic conformal field theory, and he's from IIT Roorkee. Rajesh, please start.
Yeah. Okay, thank you very much. Okay, so I hope everybody can hear me clearly. And first of all, I'd like to thank the organizers for inviting me to speak here. So I'm going to talk about this work, some work which I'm doing in the context of non-relativistic conformal field theory. So this is a title, some aspects of non-relativistic conformal field theory. And this work I'm doing with one of my past master student, Ramadevi Singh, and I'm hoping that this will appear very soon. Okay, so let me begin with a very brief introduction. So one of the things which we all like in physics is a symmetry. And the reason for it, and this has played a very important role, finding a symmetry in a system. And the reason for it that the symmetries actually enable us to simplify the underlying problem and be able to make various quantitative statements about the system under study. Okay, so now one particular symmetry which is interest, for example, in this community is the scaling symmetry. Okay, so the scale symmetry if you have a scale symmetry in a system, it is very interesting because what happens because of the scale symmetry that the various we don't need to so there is a universality. What we find universality in the system, and what it means that the precise details of microscopic thing we don't need to worry about, and we can still say a lot about the system, critical behavior of the system just based on this universality. And one special case of this scale symmetry is a conformal symmetry. And what we expect is that a system with conformal symmetry can be described by conformal field theory. Okay, so this conformal field theory, as a result, has a special significance in the space of all quantum field theories. And one of the reasons, and this is widely, it is it has quite a wider application, ranging from string theory to condensed matter physics, statistical field theory. And one of the reasons is that if you have a system with conformal invariance, then it imposes restrictions on the form of the correlation functions. And also what we have learned from last 10 years or more, that we like using the bootstrap, etc. So it can constrain the spectrum, for example, the scaling properties of spectrum, like scaling dimension, etc. Okay, so so this is what the conformal field theory. That's why we have we are very fond of it. Now, so most of the conformal field theory which we used to talk about is a kind of conformal field theory where, let's suppose, if you think of when you realize on some geometry, then in this conformal field theory we have space and time are at the equal footing, in the sense that they have a same scaling behavior. So I will call this kind of conformal field theories relativistic conformal field theory because of this scaling nature. But then there's another class of conformal field theory which has been studied quite a lot in the past for various reasons, and that is what I'm going to call non-relativistic conformal field theory. And the reason I'm going to explain why we call it non-relativistic conformal field theory. So so one of the property of this thing is that there's a variation. There's a different way the time and space coordinate scales under scaling transformation. So this gives rise another critical exponent, which is called anisotropic exponent. So for example, let's suppose if you have a system with this anisotropic critical behavior, then let's say 2-point function, if you calculate, then this will have this kind of 2-point functions where we have theta parameter, where the time coordinate scales with lambda to the power theta, and space coordinate will scale with some lambda. And this theta.
Rajesh, can you go full screen?
Sorry. Okay. Yeah. Is it fine now?
Yes.
Okay. Thanks. Sorry. Yeah. So so then we have let's say if you cover 2-point function, then this will have this kind of scaling property where time and spatial coordinate will scale differently, and delta here is scaling dimension of this 2-point function. Let's say green function. And this, what we are interested in, I'm interested in right now, for especially this talk, is the case where theta is not equal to 1. Okay, so this kind of system are called a strongly anisotropic critical system. So one particular case of this anisotropic critical system is the one where we have this critical exponent theta, the value of it equal to 2. Okay, so this kind of system is described by Schrödinger invariant field theory, and I'm in for my talk, and I will call this kind of field theory a non-relativistic conformal field theory. So I'll explain in the next few slides why we call it why this nomenclature conformal here. But this is a kind of thing which I will talk about, the value for which the critical exponent this theta equal to 2. So one particular motivation of this is that this kind of theory has an immediate application. For example, in experimentally achievable system, one like system is like unitary Fermi gas, where we have a system of fermions, free fermion, ideal dilute gases, fermion gases, which are cooled to quite low temperature. And this system, it is experimentally achievable, where we can remove all this length scale, whatever length scale appears in this system, we can get rid of all those things. I mean, we can fine-tune the system as such that the system has a scaling property. Okay, and what we expect that this system can be described by a non-relativistic conformal field theory. Okay, so one more. So I will talk about non-relativistic conformal field theory, but a more special case of non-relativistic conformal field theory, which is a conformal field theory with boundary. So so the motivation for this again, I mean, we have been seeing this conformal field theory with boundary in various areas of physics, like wave string theory or condensed matter system. I mean, from the condensed matter perspective, this is much more natural because all the real system comes with boundary. So it is very important, therefore, that if you want to study some statistical system, then it is important for us to understand, and let's suppose near the critical behavior, near the critical point, then to understand the quantum field theory with the boundary. Of course, mathematically also, and from theoretical physics point of view, it's of course interesting to understand, but also for a real system, this is natural to study. So, and one of the things to look for in this case is that when we have a statistical system near this critical point, then with boundary, then we encounter critical exponents, which of course there will be bulk critical exponents, but then there will be also new critical exponents, which are due to boundary and not necessarily related to bulk critical exponents. So these are the quantity which I look for. And it is a not new subject. People have been looking for this. People have been studying this subject. For example, like a renormalization group flow in this case, and then also monotonicity theorem in the presence of boundary. And if you restrict ourselves to conformal field theory, then with boundary, then in the last few years, there has been a renewed interest. And one of the quantity which people are interested in is complete trace anomalies. And trace anomalies have now become a richer structure. For example, if you consider three-dimensional conformal field theory with boundary, then three-dimension doesn't have a trace anomaly, but because of the boundary, we have a contribution to trace anomaly. And then people have been studying, so the new terms now will have a new central charge, and people have been studying what are these central charges, can we constrain them, etc. So my interest, my motivation in this direction is to see even for non-relativistic conformal field theory, can we extend these results? I mean, what we know about the relativistic conformal field theory, can we extend this to at least some part of it to non-relativistic conformal field theory in the presence of boundary? Okay. So before going ahead and describe in a bit more about non-relativistic conformal symmetry or Schrodinger symmetry. So let me give an explicit example where I would expect a non-relativistic conformal field theory with boundary to appear. So this is a very simple system. So this is a system of fermions, two component fermions. So when I say fermions, in this case, non-relativistic fermion, this is Grassmann odd. So so this is a free fermion. So we have a just trivial free fermion system. So this is trivially conformal theory. But now I make it interesting by putting some interaction at the boundary. Okay, so this is some point-like interaction at the boundary. Okay, which is localized at boundary. And then what we can look for is the renormalization group flow in this system and look for the fixed point. So, for example, in this case, this system has this coupling G has a dimension, marginal in the dimension t equal to 1, and therefore we can look for Wilson Physics fixed point in the epsilon expansion. So let's say in d equal to 1 plus epsilon, and we do find a fixed point where G star equal to pi epsilon over 4. So, so for epsilon small, we can study the properties of this fixed point, like operator spectrum, and then the scaling dimensions, etc. And then, and then we can extrapolate to epsilon equal to 1. And what we expect that will describe so that will give rise non-relativistic conformal field theory. And not only non-relativistic conformal field theory, but interesting non-trivial non-relativistic conformal field theory in the presence of boundary. Okay, so that's one system which is my interest, but I'm not going to describe in this system, but rather I will talk more generally, rather than focusing on a particular model. Okay. Okay, so let's come to what is this non-relativistic conformal symmetry. Okay. Let me introduce this non-relativistic conformal symmetry or this Schrodinger symmetry in the same line the way we introduced the relativistic conformal symmetry. So the very simple way of introducing this relativistic conformal symmetry is just looking at the Maxwell equation or let's say massless Klein-Gordon equation, and then look for the symmetry, okay, of these equations. In fact, actually, the relativistic conformal group, what we know is nothing but the symmetry group of this relativistic, this massless Klein-Gordon equation. Okay, so in particular, these are nothing but space-time transformation together with some action on the Klein-Gordon field, which map one solution to another solution of the Klein-Gordon equation. Okay, so this group consists of, as we know, Poincare transformations, the scale transformation, and spatial conformal transformation. And if you look for the 3 spatial dimension plus 1 time, then it is a 15 parameter group. Okay, so this is how. So this is one way of thinking about the conformal group. Just looking at the symmetries of the massless free Klein-Gordon equation. So if you follow the same line, then we can define also some symmetry group, which is let's call it Schrodinger group, which I will motivate why we should be calling also a non-relativistic conformal group in a moment. So so let's start with the Schrodinger equation, free Schrodinger equation, and then we look for the all possible symmetries which leaves this Schrodinger equation invariant. Okay, so this gives rise a group of transformation. This group has space and time transformation, which leaves this Schrodinger equation invariant. More generally, to also include the transformation, the action on the field as well, which map the Schrodinger field, which map one solution to another solution of the Schrodinger equation. So this has also been studied in the past, and this consists of, when you look for the symmetries of the Schrodinger equation, then it consists of Galilean transformation, dilatation, and expansion transformation. So I will give the explicit representation of this in the next slide. So so if you look, for example, in 3 spatial dimension plus 1 time, then it is a 12 parameter group. Okay, so it is a smaller group than the relativistic conformal group. Okay, and however, we'll see in the next slide that even though it is smaller, but then still we can say a few things, or we can still constrain many things, not many things, but at least few things like correlation function, etc., using this Schrodinger invariance. Okay. Now, there's one important thing I want to emphasize here, that usually in a conformal theory, a relativistic conformal theory, we don't have any dimensional full quantity like mass. Okay, because that will break the conformal invariance. However, unlike that, we have in the Schrodinger equation we have a mass. So actually, this is not a problematic thing, because actually in the non-relativistics thing, we don't have a speed of light as a dimensional full parameter. Okay, so therefore, as a result, this mass and the length, the dimensionally they are not equivalent. Okay, so therefore, so even though there is a mass in the Schrodinger equation, still we have a conformal invariance. Okay, so let me tell you what is the realization of this various space-time transformation which leaves Schrodinger equation invariant. So this is a Galilean transformation. So Galilean transformation include this rotation, then boost, and then space translation. Then we also have a time translation. So that constitute Galilean transformation. Then we have a scale transformation, which is nothing but spatial coordinate scaled by lambda, but then time coordinate scaled by lambda squared. So that's the theta equal to 2, the anisotropy exponent. And then we have an expansion transformation, which looks like this form. I'm not so sure you can see my cursor or not. I'm not so sure, but okay. So this is expansion transformation. Now, this expansion transformation is very similar to, at least in the spirit, a special conformal transformation. Of course, there is a difference. And the difference is that the expansion transformation is just one parameter group, one parameter transformation, just parameter beta, whereas a relativistic special conformal transformation, it carries a space-time index. So we have as many relativistic, special conformal transformation as the dimension of space-time. So here we have just one. Okay. And that's the big difference. But nevertheless, in the spirit, it is very similar because you see that the expansion transformation, I can write it as IHI, where I is inversion, very similar kind of inversion which we see in the relativistic setup, and H here is a time translation. So, this is the action of the Schrodinger group on the space-time coordinate. And this action, together with the action on the Schrodinger field, leaves the Schrodinger equation invariant. So this action on Schrodinger field looks like this manner. So this Schrodinger field is a free Schrodinger field here. So this so you see that under scale transformation, it scales by lambda to minus d over 2. So d over 2 is a scaling dimension for free Schrodinger field. And then there is also action boost as well as the expansion transformation on the Schrodinger field. Okay. Okay. So now let's come to algebra. So the algebra of this Schrodinger. Okay, so the reason. Okay, so sorry. So the reason. We are calling it a non-relativistic symmetry also because of this scaling symmetry. So this Schrodinger group contains a scale transformation, and because of that, I'm calling this also non-relativistic conformal symmetry. Okay. So now let's talk about the algebra. So the algebra here will consist of. So we can find by the commutation relation. The commutation relation will involve, so if you compute, then it will involve Galilean algebra together with some other algebras, which include the scale transformation generator D and the expansion generator C. Okay. However, when you realize this algebra on the quantum Hilbert space, the physical Hilbert space, then the physically relevant situation is the one where we have a centrally extended Galilean algebra. Okay, so this central extension is allowed by Jacobi, and we consistent with Jacobi identity. So this central extension is given by the UN generator, which is called the particle number generator. So this appears explicitly in the commutation relation between the momentum and the boost on the right hand side. But there is no other central extension. Yeah, other central extension, if you allow, that is not consistent Jacobi identity. However, this is the only consistent Jacobi identity. So this is so therefore the Schrodinger algebra consists of centrally extended Galilean algebra together with other algebra which is obtained which involve the commutation relation between the dilatation and expansion transformation with other generator. There's one just to mention here that there's a subgroup of the subalgebra of this Schrodinger algebra, which is also SL2R. So the SL2R is also present here, and one can use also this SL2R. So I will not talk about this SL2R and the consequence. I mean, if we just use the SL2R, then what people have been studying this SL2R just. But okay, I will not talk about this SL2R in my talk. I will just talk about the full Schrodinger invariance. Now, actually, there's one important thing which I want to mention here before coming to representation of this algebra. That there's one another non-relativistic people have been studying, which is a Galilean conformal field theory, which actually nothing but which one can obtain. There's a well-defined way of obtaining this, starting from the relativistic conformal symmetry, and that doesn't change. There's some sort of contraction that doesn't change the number of generators, etc. However, there's, at least in my knowledge, I'm not aware of any such construction for Schrodinger symmetry. However, the Schrodinger symmetry, one can relate it to non-relativistic conformal symmetry. In fact, one can embed it in the relativistic conformal group and we can see this in a very simple way. Okay, so we can embed it, but not in the same space-time dimension, but in one higher dimension. Okay, so let me explain this in a moment. So let's come back to this again, this Klein-Gordon equation. So, but in one higher dimension, that is d+1 spatial plus time direction, that is d+2 d+2 Minkowski space. So we have this Klein-Gordon equation, and then we can use this null coordinate, and then we can write the Klein-Gordon equation in terms of this null coordinate. Now I see that if you write this Klein-Gordon field in this form. So if you define my psi field, which is related to Klein-Gordon field by this phase factor, then you see that for psi field, so here psi field doesn't depend on the x minus coordinate. It depends only on the x plus coordinate and the rest of the position coordinate. Okay, then we see that this psi field satisfies this equation, the lower equation. And if you identify this x plus with the time, then you see that this is nothing but a Schrodinger equation. Sorry, Chandrasekhar, do you have a question or something?
Yeah, just around 5 minutes left. So.
Oh, sorry, 5 minutes left. Okay.
Yeah.
Sorry, 5 minutes left. Okay. Okay. Sorry. So this is the Schrodinger equation, and then you see clearly here that this Schrodinger symmetry can be embedded in the Klein-Gordon equation. And the only thing we have to do is look for the generator of the original relativistic theory, which commutes with the generator, which do a translation along the x minus coordinate. Okay, so this is a p plus coordinate, p plus momentum generator, which generates x minus to x minus plus c. And then we have to look for all the generator of the conformal group, which commutes with p plus, and that actually is subalgebra, which is Schrodinger algebra. And now this p plus, which commutes with the rest of this algebra, will act like a particle number generator. Okay. Okay. So now there is a representation of the Schrodinger algebra. So the representation exactly follow the same manner as the relativistic conformal field theory. Basically, we have primary operators and then their descendants. The primary operators are again state of dilatation, particle number operator, and angular momentum. So for example, this is a scalar primary operator. And then we have a descendants. So here descendants are constructed by acting momentum and the Hamiltonian. So Hamiltonian shift the scaling dimension by 2, and the momentum shift the scaling dimension plus 1 unit. So this is how the representation we can organize. So let's come to correlation functions. So the correlation function again we can obtain by just requiring that the correlation function follow Schrodinger invariance. In other words, we have to just solve the Ward identities of the Schrodinger symmetries. So this gives us a Ward identity, gives us a differential equation, and we can solve it explicitly. So for example, if we solve for 1-point function, it comes out to a 0. 2-point function has this kind of structure, and however, if we compute 3 and higher point function, then it turns out we cannot fix it completely. And this is how the difference comes in between the relativistic and non-relativistic. The non-relativistic is smaller group. So we see that, for example, 3-point function, we cannot fix it completely. We can fix up to some function of v, where v is some cross ratios, which is a Schrodinger invariant cross ratio. So now let's come to the effect of boundary. So when we consider, so the boundaries again, so I don't want to, let's not motivate, let's not give me the motivation. So, but when you consider boundary, the conformal symmetry is broken, and it is broken to a certain subgroup, And this subgroup is the one which preserves the boundary. So for example, let's suppose if we consider a conformal theory on a geometry, on a flat space with a boundary at, let's say, one of the coordinate y equal to 0, then in that case, my reduced conformal symmetry will be the extended Galilean symmetry of the boundary together with the dilatation and the expansion transformation. Okay. And now what I'm interested in, see that what are the effect of this reduced symmetry on the correlation function. Okay. So again, we do the same manner. We solve the water entities of the reduced conformal symmetry. So now we find that, for example, one point function is not equal to 0 in a 0 particle sector. If particle number is not equal to 0, then the 1 point function is still 0. But however, if particle number is 0, then there is a non-zero 1 point function. 2 point function here we can determine, but there is here we cannot fix it because there is a cross ratio xi, which is function of y1, y2 or t12. So y equal to 0 is the boundary. So this is a bulk 2 point. This is a bulk operator and the 2 point function. And what one of course clearly expect that when this 2 point function of bulk operator, when we take the this y coordinate far away from the boundary, then the full sorting invariance should reach to. Okay, that is z xi should go g of xi should goes to 1 as xi approaches infinity. That is a bulk limit. Okay. Okay, now so we have, this is the 2 point function bulk operator, but now since we have boundary, so now we have a richer structure, and that there are operators which are localized on the boundary. Okay, so these are the boundary operators, and now we can also try to see the correlation functions between bulk and boundary operator, and this will give rise to some new critical exponents. Okay, so this is the 2 point function between bulk and boundary operator. OHAT is a boundary operator, and this you can fix again by solving the water entities. In fact, actually, this relation is first. This correlation is important because this also tells you an important thing, that this bulk operator can be expanded in a series expansion in terms of boundary operator. And this we see because if we expand this right hand side in powers of y, the y1, which is y1 is the bulk coordinate, the coordinate of bulk operator, then we have this series expansion. And if you use the 2 point function of the boundary primary operator, which is given like this, then we see that that the bulk operator can be given an expansion, series expansion in terms of boundary primary operator and their descendants. So this is the summation infinite sum. So particle number has to be same in both the side, but given particle number, let's suppose if we know all possible boundary operator, then it is sum of all these boundary operators. And then for each boundary operator, there's a conformal family which enters here. There's a descendants which enters here, where this D is a differential operator which is given by this. Okay. So this is the expansion. This is a boundary operator product expansion, and this boundary operator product expansion becomes simpler. For example, if I have a bulk operator satisfying Schrodinger equation and the scaling dimension d/2. In that case, what happens? This boundary operator product expansion receives contribution only from the 2 conformal families, one with scaling dimension d/2, another with d/2 plus 1. So this corresponds to bulk operator at the boundary value of the bulk operator, as well as the normal derivative. So these are the 2 operators which has a scaling dimension d/2 and d/2 plus 1 respectively. And this corresponds, this enters in the operator product expansion for the bulk operator, which solves Schrodinger equation. Okay. So now the Okay, so after this I'll come to the conclusion actually. Okay. So actually, so as I said that we have a bulk 2 point function. Now we have boundary operator product expansion. So therefore the bulk 2 point function. So therefore you can use this bulk operator and its expansion in terms of boundary operator in the 2 point function. And as a result, what will happen that the bulk 2 point function now can be given in terms of the 2 point functions of the boundary primary operator and their descendants. In particular, since we know the 2 point function boundary primary operator, which is given here, and we can calculate from here the descendants 2 point function, we can in fact obtain the expression for this g of xi, which is unknown function, and this in terms of this boundary data, and this gives rise to a boundary conformal block. So for example, here boundary conformal block which enters is very simple compared to non-relativistic case, which is just 0f1, and okay, this hypergeometric function with 0f1. But this is a very simple form, but nevertheless we have this boundary conformal block. Okay. So actually there's one thing I wanted to say, but I don't have time. Basically that non-relativistic system can be also placed on a curved spacetime, and this requires something called a Newton-Cartan structure. But okay, but I don't have a time to talk about this. But we can write down the action, which is a diffeomorphic and value-invariant action. We can also include boundary, which is just nothing but including some extrinsic curvature. And we can also define displacement operator, etc. So, okay, but I don't have time to explain this. So let me come to the summary. So a very short summary is that so non-relativistic systems are important to study. And what I have done here is that we have studied this non-relativistic system in presence of boundary, and we try to understand the effect of these boundaries and what are the critical exponents, new critical exponents. Okay, so we have also so as a conformal field theory, we have studied like a boundary conformal block, and in some particular models we have also analyzed this various spectrum. I'm not describing those models here, but so it will appear in my paper. But now there is a future direction. There's a lot of things one can do. So, for example, as I said, emphasized at the very beginning. So, what happens to the trace anomalies if they because there is also something trace identities. Slightly different form, but nevertheless there is trace identity. And now we have a curved spacetime, so we can study trace anomalies. And so, what is the trace anomalies and how it is affected when there is a boundary? Then the bootstrap for non-relativistic system, the monotonicity theorem. So, what happens? So, actually, this question, there's one question which I'm curious about: is that can we relate this Schrodinger correlation function with the relativistic correlation function given this null reduction which I mentioned? And then, of course, another thing, supersymmetric extension of this and partition function computation on the curved background, etc. Okay, so yeah, there are many directions. Yeah, so with this, I will stop here. Thank you very much.
Thanks a lot, Rajesh. We are running a little late. There is a quick question, or we can also take up the questions during the, I think, yeah. Gautam, please.
Yeah, I had a very short question. Whether the method of images works for
yeah. Actually, I mean, so we compute this, like, for example, Green's function, etc. Using the method of images. That's true. Yeah.
So there are the word identity like proofs for non-relativistic conformal field theory also, just like 𝗏𝗏𝗀 had done.
Yeah, actually, okay. So when I did it, I didn't use a method of images. I just directly solve it. But yeah, but it boils down to solving a differential equation, and we can use it method of images. Yeah, to
Thank
solve
you.
that.
Yeah, thanks a lot.
Yeah, Kaushik.
Yeah, I had a question about this point 4 in this page. So the answers that you took for the relativistic wave function to reduce it to the Schrodinger equation, that wave function is not normalizable, right?
Yeah, that's true.
But on the other hand, so if you want to relate these correlation functions, you are assuming that what reduction of the whatever the relativistic groups acts properly with this is a Hilbert space of representation.
Yeah,
and that is supposed to be normalizable. So don't
That's
you
true.
see a problem in connecting?
Yeah, exactly. So that's what I'm saying, that I have not seen this relation, and I'm not so sure. So I don't know exactly. Maybe maybe you have answered this, that we may not. Actually, that's why in many of the literature people just study independently this Schrodinger.
That is fine. That is fine. But what I'm afraid is that this reduction as it is will not give me a proper representation of the
that's
relativistic group.
I see. Okay.
Take me away
Thanks,
from it.
Yeah. Okay. Thanks.
Yeah, Arnab, you had a question.
Right. Should I ask the question or maybe postpone it for the discussion? Because
okay, maybe then.
Actually, Chandra, I have some urgency today because of reason I may not be available for discussion. So if there's a question, I can happily answer. Or if there's a delay, okay, that's okay.
Well, okay. Let me just quickly ask. Maybe I can touch base with you later.
Yeah,
on.
yeah.
It's just sort of a comment / question regarding the monotonicity theorem that you mentioned. I mean, generally, what seems to be the case is that because you have a less amount of symmetry, it's a bit hard to prove it in general.
That's true.
But what might happen is for large N systems, if you go through that kind of, if you go to that corner, you might be able to prove monotonicity theorems a bit more.
Okay, thanks.
This thing, but there is a risk in the sense that it might become trivial. So that is it. And my question was sort of mostly, tangential to your talk actually, because I think you talked about the cases for when the dynamical exponent is 2, right?
That's true.
The general dynamical exponents.
No, I talked about theta equal to 2.
Yeah. So my question was sort of that: how much of this you expect to kind of carry on for when theta is not equal to 2?
Actually, okay. So first of all, I was looking for the literature. Maybe you can help me in this. So what we know about away from theta equal to 2? Okay. So do we have a conformal invariance, or at least the group where we have a scaling symmetry, etc.?
Yeah. We have a scaling symmetry. It's just that you don't have the special conformal or what you call this. I forgot what you call
expansion.
Yeah. So that one is gone. But scaling symmetry is certainly there, and the representations, etc., they are also perfectly fine, except that now you have a less symmetric situation.
I see.
Life is more challenging.
I
see.
But
but yeah, I mean, maybe we can talk later.
Sure.
Okay. Thanks.
So we are really running late. So a couple of more questions are there. Is it fine if they take it offline? Or if it's very quick from TIFR, QST?
It's fine. We can do it later.
Okay. Thank you.
Yeah. Okay. Yeah. Okay. Thanks.
Okay. Thanks, Rajesh. Thanks a lot.
Shreyas, if please drop me an email, because actually because of some urgency, I may not be available during the discussion session. Yeah. So okay.
Somdatta, you can also ask later, please.
I have a very quick question.
Okay.
So the question is, are there any gravity duals to this kind of story?
Yeah. So people have been studying with the ordinary symmetries. Yes. And there people have been studying the correlation functions, and there's this ADS50 kind of thing for Schrodinger theories. Yeah.
Okay, thanks.
Okay. Let's all thank Rajesh once again.
Okay. Thank you.
For this seminar.
Thanks.
So Suman, you're ready?
Yes.
Yeah.
Can I share the screen?
Please, yeah.
Can you see the screen?
Yes. So the next speaker is Suman Kundu, and will speak about bounds on Regge growth of flat space scattering from bounds on chaos from TIFR Mumbai. Suman, please.
Okay, so thank you for this opportunity. I have done this work in collaboration with Diksha, Subham, and Professor Siraj Minwala. And so today we'll ask the general question we are asking is how to classify all possible quantum S matrices. And we already know that string theory gives you multiple examples of such consistent scattering amplitudes, and because of various possible compactifications in string theory. So this makes the classification problem very difficult to pursue. But in classical limit, that is in G string goes to 0 limit, all these known consistent examples shows an universality structure in their answers, and all those answers reduces to only 3 options, and those are Einstein gravity, type 2 theory, and heterotic string theory. Now, looking at this fact, Chaudhary and collaborators has conjectured that these 3 are the only consistent gravitational S matrices satisfying some low energy constraints like factorization on poles and stability of vacuum and causality, and others also. But this is also very hard to show because you have 2 string theory options there. You can also further restrict to the constraint that you have finite number of poles and only consistent classical gravitation S matrices whose exchange poles are bounded in spin is only Einstein S matrix. So since we are excluding the infinite spin exchange, we will be only left with the Einstein gravity. So, but the previous conjectures only exclude or include some theories. But in this paper, the Chaudhary and collaborators have shown that in d less than equal to 6, the last conjecture, the conjecture 3, is indeed true, provided physically motivated constraint on S matrix is true. So they have named that as CRG conjecture or classical Regge growth conjecture. The statement of the conjecture is the S matrix of a consistent classical theory never grows faster than S square square at fixed t, that is in the Regge limit, for all physical values of momentum and for all possible polarizations. Okay. So arguments for this CRG conjecture can be found in various places, for example, in Kame's paper and also in chaos bound paper, and later it was discussed also in the sharp boundaries paper. These are the references. Today we will show that how chaos bound in the boundary gives rise to the CRG conjecture in the bulk. Okay, so we will be considering 4-point function, a tree level 4-point function for scalars and spinning particles in ADSD+1, and only generated from contact interactions. So since we are considering only 4-point function, this is our ADS cylinder, and this is the boundary, and P1 and P3 are inserted at diametrically opposite positions at time t is equal to tau, and P2 and P4 are also at same time t is equal to pi, but these P2 and P4 are also diametrically opposite, but P2, P4 and P1, P3 line has a relative angle theta. So in this diagram, you can see there are only two parameters, tau and theta, and those will be dictating our, those will be parameterizing our cross ratios. Okay. So now in this work we will fix our theta for some value, but we will be also concentrated. We will be also considering small theta limit, but we will be varying the tau from pi to 0. So let's start with tau is equal to pi. When tau is equal to pi, you can see P1, P2, P3, P4 both all four are at the same time. So that is the Euclidean configuration. Okay. And then you start from there, and then you decrease your tau from pi, or you will reach a position, you will cross pi minus theta, and then you will reach a position where P1 and P4 are time lag related and P2 and P3 are time lag related. Others are space like all other combinations are space like related. So that is exactly the causally Regge configuration where the chaos bound is valid. Okay, so this is the place where chaos bound is valid. And you can take this P1 and P3 further down, that is you reduce your tau, and then if tau crosses theta, you come into this place. Okay, this is the configuration when tau is less than theta. So that is the place where P2 and P4 both are in causal future of P1 and P3. Okay, this is the causally scattering region where a Barth scattering can take place since both the future particle are in the causal future domain of P1 and P3. So this is where our CRG will be valid. So we will be taking information from this chaos bound from this causally Regge configuration, and we will relate it to the CRG conjecture valid in the causally scattering region. Okay, so now here I will explain the rough sketch of the flow chart of the proof, how we have done this. So since we have said that tau and theta are the two parameters in our problem, we will be defining this parameter A, which is a ratio of this tau by theta. Okay, so A is related to this rho parameter, and the conventional cross ratios are Z and Z bar. We are taking sigma and rho instead of Z and Z bar, which has this simple relation. So and rho is related to A. So if A is, so as you said that if tau is less than theta, we are in the causally scattering. If tau is greater than theta, we are in the causally Regge. So that means A is greater than 1 is causally Regge, A is less than 1 is causally scattering. Okay, so A is equal to 1 is the light cone, there is a light cone singularity, and you have to cross light cones if you cross A is equal to 1. Now, what we have done, that we have taken that 4-point function for spinning particles, and we have calculated that in sigma goes to 0 limit. Sigma is one of the cross ratios. You take sigma goes to 0 limit. This is conventionally known as Regge limit. Okay, so if you take sigma goes to 0 limit in the 4-point function, you will be exploring the Regge limit for fixed rho. So you can show that for both the configurations. So these configurations are parameterized by rho, but sigma can be taken to 0 in both the configurations, and you can see that the form of the function remains same. That is, the sigma behavior remains same, but there is a change in the function for causally scattering or causally Regge. Okay, so this rho function changes, but we have shown that these two functions are analytically related. So you can define a grand function for any complex A in the upper up plane, and you can relate these two functions as a limit of that grand function as a limit from the above, and you have to approach the real axis. Okay. Now in the second step, instead of sigma goes to 0 limit, we will take rho goes to 0 limit first. Okay, that will access the bulk point limit. So in the bulk point limit, we know there a bulk point singularity arises in the causal scattering. So since we are taking A goes to zero limit or rho goes to zero limit, this actually this can't go to the causal regime. It is always in the causal scattering. So these two things are calculated in the same regime, right? So that's why this causal this GCS or causal scattering of e to the power 2 rho must have this singularity, and we have checked that is true. Okay. Next, we have shown that the coefficient of this bulk point singularity is related to the flat spaces matrix that is happening in the bulk. So, as we said that in the causal scattering regime, in the bulk, the scattering can take place. We have localized the the scattering in the very small region in the bulk, and that F sigma is related to this flat spaces matrix. Okay. So later, after taking this rho goes to zero limit, we have taken sigma goes to zero limit again. Okay, that is, we are again accessing the Regge limit, but in reverse order. So there, this bulk point singularity will persist, but this F sigma has this sigma behavior, and accordingly, the flat spaces matrix will have this h to the power a behavior. We have shown that this, if the corresponding flat spaces matrix in the bulk, if this has h to the power a behavior, the corresponding bulk 4-point function in the boundary 4-point function will have this sigma to the power a minus 1 behavior. Okay, so this equality we have checked. Now you can see that both these limits, that first taking rho goes to zero limit and then sigma goes to zero limit, and previously we have taken only sigma goes to zero limit first. So since there is a commutation of limits, the sigma power is in general different. Okay, this can be different, but we believe for many cases this is equal. But we have explicitly checked that a must be less than equal to a prime. Okay. This so in known cases a is equal to a prime, but it is definitely true that a is less than equal to a prime. And also, since now this path is totally clear for the proof, that we have said that in causal Regge regime the chaos bound is valid, and that says that a prime must be less than equal to 2. So this is a statement for the chaos bound paper that a prime is less than equal to 2. So that constrains this a prime, and accordingly that this a prime in this causal scattering regime, and this causal scattering regime, a sigma behavior is related to this sigma, and that gives you this relation. So that leads to the final step, that is a is less than equal to 2. So where we have seen this a is this part. So that is the flat space S matrix. So flat space, if the in Regge limit flat space S matrix goes as h to the power a, this definitely it should grow slower than s square. So that says that if any interaction in the boundary violates chaos bound, that will definitely violate CRG. Okay. I will roughly go through the first and the second step. That is the Regge limit and the bulk point limit. The first one is the Regge limit. If you take the Regge limit, this h is that grand function which is the function of complex A, and that reduces to GCS and GCR. That is the causal scattering 4-point function or causal Regge 4-point function. So this is the a particular analytic function, and here we are showing the analytic continuation you have to do. The upper region in this in this e to the power 2 rho variable access the a greater than 1 region, and this is the a less than 1 region. You start from a greater than 1 answer and then do this analytic continuation, you reach the another answer. So that means if a function is not 0 in the causal scattering region, it will not be 0 in the causal Regge region. So this is a very important statement which we have used in the proof. Okay. So now this is the bulk relation to the bulk point singularity with the boundary correlation structure. Here you can see that this is the only place where it depends on rho, and this is the same bulk point singularity. Everything else depends on sigma. Okay, everything else is fixed except this function. We will explain what this function is, and this the whole coefficient of this rho to the power this bulk point singularity is f of sigma we have used previously. So how to calculate this S tilde is, first you start with the you take the flat space S matrix and calculate the flat space S matrix with these proposed polarizations, or for the scalar field you use e to the power ik. Okay, and these are the boundary polarizations. So you use this and divide by the omega to the power r, that is the energy to the power r, if you have r derivative in the interaction. Okay, that you take, and if you divide it by this omega to the power r, this is only function of theta, and that input you put. So this is the input from the flat space bulk, and then you get the boundary correlation structure. Okay, so this is how it is related to the, so boundary correlation structure is related to the flat space in leading order. For the scalars, it matches with the previous result derived in this references. For the spinning cases, we have derived it. So to summarize, we have done this calculation for this contract interaction only for the massless particles. So it is very important to see that the same conjecture holds true for the exchange diagram, and whether it's true or it violates in the loop diagram. That is we are doing right now. We have taken now a very important point in this proof is we have taken flat space limit of ADS and ADS CFT conjecture to show just and also quantum structure of the boundary to show a classical theorem in the bulk. Okay, so it would be very satisfying to get a direct bulk argument in flat space, which will also be true for the flat space or DS. Okay. It is also interesting to see that you just put the classical string scattering amplitude instead of that S tilde, and then what kind of boundary structure it keeps. Okay, and then the next very important thing is to go for the quantum Regge growth conjecture, which says that the S matrix cannot grow at all, and it will be bounded by S to the power 0. Sharp boundaries paper gives a very good starting point for this quantum version, and also it will be very important to see what happens for the massive external particles. So we have assumed massless particles in the problem. We should use the massive particles. One problem with the massive particle is there is a huge energy separation between the longitudinal mode and the transverse mode. So the ADS curvature gets mixed up with the transverse mode S matrices, and it is very hard to filter only the transverse mode S matrix. So thank you for the.
Thanks, Suman. Questions, please. Yes, Arnab, please.
Hi. So I have a very quick question, probably. So you talked about essentially some connection between scattering, how Regge growth should happen with the chaos bound. My question is sort of tangential to this, but so whenever you talk about chaos bound, etc., it's in terms of some correlation function, which in the field theory or in CFT involves some complicated contour like Keldysh, etc., right? So is there a geometric way of seeing what might be happening in the bulk scattering process corresponding to that that contour structure? Is it possible to see this Keldysh contour structure in the bulk scattering somehow? Or is that a bad question?
Yes, definitely. No, the chaos bound calculates only OTOC. Okay, so there is the bound is on the OTOC, but you can do a code, you can do an analytic, you can go to Hilbert space, and the same insertion points which are OTOC in the angular quantization becomes a time-like correlator in the bulk. Okay, so in the Hilbert space it becomes time-like, not time-like but time-ordered correlator. So and that's how it is related to the scattering amplitude you are calculating in the bulk. So that is actually discussed in the appendix of that chaos bound paper. That I mean, you can access the time-ordered correlator from the OTOC using Hilbert coordinate transforms.
Okay. I actually had slightly different thing in mind, but okay, maybe I can ask you later. Okay, thanks.
Arnab, maybe I could just say sure, what Suman said again, but maybe say it again, which is that whether something is time ordered or out of time ordered depends on your definition of time.
Yes.
Now, suppose we take a two-dimensional plane and we do an angular quantization or an ordinary quantization.
Okay.
So a path integral that represents an out of time ordered correlation function in angular quantization could well represent a time ordered correlation in ordinary quantization. And this is the case in this situation. The situation is out of time ordered in angular quantization, which is where you use the chaos bound, but it's ordinary time ordered in just global quantization, which is where you use the scattering.
Yeah.
Okay. I see. Okay. Thank you.
All right. If there are no other questions, let's thank Suman again for a nice quick summary of the work.
Thank you.
Ayan, you're next.
Yes.
Yeah, so it's 13 minutes plus 2 minutes for question answer session.
Okay, thank you.
Yeah. So Ayan K. Patra, he will speak about black hole interiors as trans-IR holographic RG flow from SINP Kolkata.
Yeah, thank you. So let me first thank the organizer for giving me an opportunity to speak about my work in this wonderful conference. So title of my talk is Black Holes Interiors as Trans-IR Holographic RG Flow. This is an ongoing work in collaboration with Elena Caceres, Amitabh Kundu, and Sanjay Shoshi. So the outline of my talk is the following. First, I will give a brief introduction and try to motivate. Then I will talk about this holographic A function. After that, I will talk about the thermal A function and about this quantum information and the trans-IR flow. Finally, I will conclude and talk about the future directions. So what we are trying to do is that we try to study the holographic RG flow in the interior of a black hole by analytically continuing the radial direction. And we know that this radial direction in the bulk theory is related to the analogous to the energy scale in the boundary theory. So in QFT, one may analytically continue a non-trivial renormalization group flow beyond its infrared fixed point to a trans-IR section of the flow by complexifying the energy. One very particularly interesting quantity in Einstein gravity that decreases along this flow is the A function, and we try to give a thermal analog of this A function, and guided by this A function, we ask three very specific questions. So first one is that do the trans-IR flows obey a monotonicity condition? Second being, what characterizes the end point of the trans-IR flows? And the last being that how does the trans-IR flow relate to quantum information? Before I'll address this question, let me give a brief introduction of the holographic K function. So we start with the Einstein gravity in d+1 dimension coupled to various scalar field with this following action, and this potential has a number of extrema at those points, and at those stationary points, the solution is just the ADS d+1. Now let us consider a solution where the scalar sits at the UV fixed point near the boundary and makes a smooth transition to an IR fixed point in the interior. This transition can be thought of as holographic version of the RG flow, and from the boundary field theory perspective, the boundary CFT flows from the UV fixed point to a IR fixed point. Now one usually considers the domain wall unsatch for such holographic RG flow, which is given by this following metric, and one defines the A function by this way, which depends on this work factor, and using the non-relativistic condition, which says that this you take any null vector when contracted with the bulk energy tensor, and one can show that this A prime rho is always greater than or equal to 0, which implies that this A function or A is a monotonic function in the radial direction. So in other words, this AUV is greater than or equals to AIR. Now, what we are trying to say is that we propose a thermal analog of the above A function, which is this we call this AT rho, and which is given by this formula, and we choose the metric unsatch to be this domain wall type unsatch, and we set the location of the horizon at rho equals to 0, and the boundary is at rho equals to infinity. Now with this function, one can show that this the thermal A function is the same for the vacuum ADS d+1 and ADS Schwarzschild, which is a consequence of the both geometries being dual to states of the same UV-CFT. Now we use the null energy condition and show that this A prime rho is always greater than or equals to 0 for rho greater than or equals to 0. Now to go inside the to access the interior of the black hole, one can do this analytic continuation where one sends the radial coordinate to some ik. But we find that it is computationally easier to consider different ansatz. So we take a different ansatz to show the monotonicity in the interior region. So this ansatz is deformed area Schwarzschild near the boundary, and it is Kastner universe near the singularity. So R is R equals to infinity is the singularity, and R equals to 0 is the boundary. Now, using the same null energy condition, we find that this A function, or the thermal A function, decreases along this trans-IR flow direction, which is the interior of the black hole. So we can say that this A function is a monotonic function of the entire flow, answering the first question. Now this is the cartoon for such flows. So this red, so this black arrow represents a conventional UV2 IR holographic RG flow, whereas this red arrow indicates a trans-IR flow parameterized by a time-lag radial coordinate. Now this, if we use this, try to find this A function in the Kastner-like solution, we see that this A function, this is the form of the A function, and in the Kastner regime, where this R tends to infinity, the chi function blows up. So the chi function blows up as a for that reason, this this thermal A function vanishes at the singularity. So it might indicate a total loss of degrees of freedom in the CFT state. So it answered our second question. So this is a numerical plot for the A function, thermal A function, plot with respect to the radial direction, and phi0 by t is the deformation parameter, and phi0 by t equals to 0 represent that there is no deformation of the CFT state. So it starts from a maximum value, and it monotonically decreases and become 0 when R tends to infinity. Now we try to answer the third question, which is that how does the trans-IR flow relate to quantum information? So we take two proposals for complexity equals to volume and complexity equals to action, and we find that in the picture of complexity equals to volume, the codimension 1 slices can never probe the region near the singularity region. They stuck at some critical radii, which I call RC, and at these late times, when the boundary range tends to infinity, the rate of change of this complexity or the maximal volume is related to the thermal A function. So this thermal A function has the knowledge of the growth of the complexity at the late time. So next thing we try is the complexity equals to action. So for the complexity equals to action, what we do is study. We evaluate the action on the WDW patch, and there exists this null joints, which is just the null rays meeting at the interior point, interior region. So there exists some boundary time after which these null joints exist, and so this is the late time picture. There's this null joint exists, and within this 0 to TC, within this 0 to TC limit, we take this space-like symmetric geodesics, which is related to the turning point. So what we can say is that this turning point is can be mapped to the boundary time. So we have these. For late time, this turning point is mapped to the boundary time when TB is greater than or equals to TC. And for this 0 to TC, this the interior point can be mapped to the boundary with this space-like geodesics. So one can say that these null joints are a good probe to the trans-IR flow for TB greater than or equals to TC, and space-like geodesics are a good probe when this region is 0 to TB to TC. Yes. And so the conclusion and the future directions are following. So we have constructed a candidate for the A function, which is monotonic along the entire flow. And this thermal A function vanishes at the singularity, indicating they might indicate a total loss of degrees of freedom. So the interesting future directions are following. So we can study this 18 more examples of the flows, which is the higher order scalar interaction, vectors, etc., and an analogous extension of the thermal A function to higher curvature theories. Thank you.
Thanks, Ayan. Questions, please. I think there is a question from TIF. Okay, I was just wondering, what about the...
Hello?
Yeah.
Yeah, sorry, I have a small question. So this AT quantity that you defined,
yes.
So you mentioned something that it should correspond to in the boundary side. Could you please elaborate on that?
So this point.
Yeah, no, I mean, this AT that you identified, which is a monotonic quantity, what do you think? Yeah, what do you think corresponds to on the boundary?
Okay, so so actually this AT in the so we are probing in the interior of the black hole. So so in that sense, that so AT.
So by complexity, I thought you meant some kind of complexity on the boundary, or maybe not. I don't know.
Yeah. Sure. So the complexity at this so this AT at the evaluated at this RC just tells you about this growth of the complexity.
Oh, I see. So and then further you use this other dictionary which is proposed, which says volume should be equal to complexity, and that's how you want to relate it to this boundary quantity. Okay, I see. Thank you.
Can I make a very quick comment just to so just to sort of repeat what Ayan said, I think if you take just the standard Regge geometry, this AT is exactly the central charge of the dual CFT. Nothing surprising. Even if you take empty ADS or you take Regge-Schwarzschild, it's just the central charge of the CFT. But when you deform it with a relevant operator, like what is being done here, then of course the entire geometry changes, including the inside of the black hole. So the point here is, I think, Ayan is trying to make is that there is the same AT function that you could have defined would actually have a monotonically decreasing property inside of the black hole as well, and along a direction with which you can connect features like complexity, if you believe these proposals and so on and so forth.
Yeah.
Okay.
Thank you.
So if there are no further questions, let's thank Ayan once more. Very nice. So our next speaker is last talk of the session is by Sabyasachi Maulik.
Hello.
Yeah.
Is
Speak
my
about
screen
entanglement
visible now?
entropy and the first law at third order for boosted black brains. Yeah, it's visible. Please go ahead.
Thank you. So hello and good afternoon once again. My talk is based on a paper from last year with Dr. Harvendra Singh, and it is on entanglement entropy and the first law at third order for boosted black brains. So by now it is well established in the ADS-CFT community that the entanglement entropy associated with any subregion in the boundary conformal field theory is related to the area of an extremal codimension 2 homologous surface in the bulk gravitational spacetime. In a series of works, it was shown that the perturbative change in entanglement entropy between empty ADS and any perturbed asymptotically ADS geometry admits a relationship which is similar to the first law of thermodynamics. This relationship is usually expressed in the form of equation 2, where delta E on the right-hand side denotes the change in energy of the subregion, and the quantity TE is called the entanglement temperature, which for asymptotically ADS geometries depends on the inverse of the characteristic length of the subregion. It is also expected that in presence of other conserved charges in the theory, the first law will include their contributions. The goal of our present work was twofold. We wanted to do an explicit computation of holographic entanglement entropy in the presence of a chemical potential-like term. And we also wanted to work out a possible first law-like relationship, which includes contribution beyond leading order in the perturbation theory. The holographic calculations were performed using a boosted ADS black hole spacetime. The boost was applied in the y direction, and the same is considered to be compactified over a circle of radius ry, so that if we perform a Kaluza-Klein reduction and come to lower dimensions, we would perceive a Kaluza-Klein gauge field, which is denoted by omega. For the holographic entanglement entropy calculation, we chose a subregion in the shape of a strip. The strip width is along x1 direction and is denoted by curly L. The other directions are unconstrained, but we put a large cutoff, capital L, to avoid any divergence. To find out the entanglement entropy, we need to calculate the area of an extremal surface, which is usually done by solving an area integral. Unfortunately, this integral cannot be solved analytically for any general spacetime dimension, so we made some approximations. We considered that the width of our subregion, curly L, is very small compared to the black hole horizon parameter, so that we can expand our area integral and any related quantities in this dimensionless ratio L over ZH and express the area as a perturbation series. And in the work, we worked up to third order in the perturbation series. So in this figure, I have plotted the difference in area with respect to ADS ground state against the width of the strip and tried to show the effect of including higher order corrections. The purple curve at the top is the area difference at leading order. The second order correction to it is negative, so the area decreases by some amount, but the third order is positive, so it increases by a small margin. And I have tried to compare it with some numerical results, and for small enough lengths, there is pretty good match. Right, so once we find out the area, we can calculate the entanglement entropy. To write out the first law, we need another ingredient, which is the stress energy tensor. And this is usually calculated by doing a Pfefferman-Graham expansion of the asymptotically ADS geometry. This expansion gives us the following expressions for the conserved charges, which are the energy, the pressure in the direction orthogonal to the boost, and the boost momentum, which is quantized. Using these expressions, it is very easy to show that at the leading order, the entanglement entropy trivially satisfies a first law-like relationship. Here, delta denotes generic variation with respect to the two parameters of our theory, which are the black hole horizon parameter, and the boost. The quantity beta E1 is the inverse of the entanglement temperature. And as expected, beta is proportional to L. However, we note that at the leading order, there is no contribution from the chemical potential conjugate to the boost momentum. Why is it so? So we define our chemical potential as the value of the Kaluza-Klein gauge field evaluated at the turning point of the extremal surface. And at the leading order, this quantity is actually of the order 1 over ZH to the power D. So a term like mu delta n is of the order 1 over ZH to the power 2D, and it cannot contribute at the leading order. Nevertheless, its contribution should not be ignored at higher orders. So to write down a first law-like relationship, including the higher order corrections, we first propose that an equation of the form of equation 10 be satisfied. Here alpha and zeta are some undetermined coefficients. To determine them, we perform variations on both sides with respect to the two parameters ZH and beta gamma square equals K, and then compare their coefficients. Okay. So after the comparison, we can express alpha and zeta in the form of some power series. And we note that at the leading order, alpha is actually equal to the inverse of entanglement temperature we found previously. Therefore, we find that it is appropriate to define alpha as the new inverse entanglement temperature at second order. And we also redefine our chemical potential in this manner. Doing so, we find that the variation of entanglement entropy can actually be expressed in the canonical first law form with the redefined entanglement temperature and chemical potential. Actually, this algorithm works for all higher orders. So at third order, we can again start with a relationship of this kind and find out some redefined entanglement temperature and chemical potential for this order using the similar procedure I talked about. And then we can show that the first law is satisfied. In this figure, I have plotted the entanglement temperature and its dependence on the subsystem length for ADS4 and ADS5 and tried to reflect on the effect of corrections. So if we consider the bare entanglement temperature, which is given by the red line, it is simply inversely proportional to L. But at the next higher order, the corrections are positive, so it increases by some amount. And at third order, the corrections would be negative, so again it decreases. So we again notice the same change in sign at every order that we noticed for example, the extremal area calculations. And this possibly hints at some kind of convergence of a series. And actually, we expect that if this series could be resummed, then the entanglement temperature for large subsystem length would actually approach the temperature of the black hole. That was the main results of the work. We also did some similar calculations for other geometries, which include the generic black DP brane, where the results can be found by doing a simple substitution. And we also considered the ADS plane wave geometry, which is a zero temperature background. And we showed that similar results also hold there as well. To summarize, we worked out some explicit examples and put forward a proposal for writing out the first law of entanglement thermodynamics at any order in the perturbation series. And we found that in order to do that, we need to appropriately, quote unquote, renormalize the entanglement temperature and chemical potential at each order. Thank you very much for your attention.
Thank you. Questions, please. So I had a question. You had a plot of area versus L, right?
Yes.
Yeah. So why is there a mismatch at higher orders in L? I mean, for large L.
So the mismatch with the numerical calculation.
Numerical.
Yes, because we are using a perturbation series approximation to calculate this area. This is not an exact calculation. So it is only valid for very small subsystem lengths.
Yeah, there is a question from TIFR.
Hi, a quick question. So in the usual first law of entanglement, it's the modular energy which shows up on the right-hand side. So
Yes.
in this case, if I understand correctly, your energy is like the total global energy, or was it the modular energy? Or if you have any comment on that.
Okay, so we are using a strip subsystem for which I don't think an expression for the modular Hamiltonian is known. So this energy is actually the energy difference between the ADS ground state and this perturbed geometry.
I see. So it's the total energy, not the
Yes.
modular. Okay. But because you're working in the small strip limit, maybe the two are related.
Yes, maybe the two are related. Actually, if we consider spherical subsystem, it has been shown that the modular Hamiltonian can be expressed as an integral over these stress energy tensor components. But for the strip subregion, such a relationship doesn't exist. So I cannot match them exactly.
Thank you.
Thank you.
Okay, so if there are no other questions, let's thank Sabyasachi once again.
Thank you very much.
Presentation. So I will hand it over to Alok here regarding announcement about the post-lunch session.
All right, thanks, Chandra. So I had sent out a text on the chat session requesting that we are going to be reconvening at 2:15, 2:15, 2:15 2:15. We're meeting on a different Zoom link, which for everybody's convenience, I have now again, I had again included in the chat itself. So let's meet at 2:15, 2:15. All right, thank you so much. Bye-bye.
Bye.
So team, I think we can end the recording, the YouTube live stream.